we didn't want to turn anyone down, so I hope everybody will enjoy hearing what everyone else is doing. Just to remind everybody, we want to keep the time slots to 15 minutes. So please try to keep your talk to about 12 minutes so we have time for a couple questions. And we have been having each person share their screen and control their own presentation. So Oriole, if you want to start, that would be great. And then at the very end, we'll have a short time for discussion. Hopefully won't drag that into too many people's lunch or dinner or whatever. Hi, okay. Welcome.
Thank you, Luisa. So let me share my screen.
Good evening to you.
Yeah, good morning to you guys, evening in the other side of the Atlantic. So yeah, first of all, I would like to thank you for giving me the opportunity to introduce to the CESM community work that we are doing in collaboration with University of Illinois and Barcelona Supercomputing Center. So this is a new package, Chemistry Across Multiple Phases, CAM, an integrated multi-phase chemistry model. Is an initiative that started with the postdoc of Matthew Dawson a couple of years ago with us at BSc. Now Matthew has joined Anchor last year. So I will introduce you a little bit what is CAMP and well, the main motivation of all this work. So as you know, main chemistry in atmospheric models is treated in different ways, and generally is a mix of different strategies. So solving gas phase chemistry in a kinetic approach, and using equilibrium from inorganic chemistry and organic chemistry, and some specific cloud chemistry, which makes the mapping between modules complex, and also the order of operation can also affect the results. So if we look on a host model where we have all the complexity with the transport, deposition, emission processes, and the photolysis rates computed and passed through the gas phase chemistry, and then using of different complexity models for the activity and inorganic and organic components. So this makes a big challenge to update and change pieces or substantially big pieces of the code, and also adding new reactions or just removing them from the system. So for that, we work in the last years in the design of CAM, that with the main idea to treat chemistry, the partitioning and related processes kinetically as one system to solve, and make it as a very flexible environment for models, and so usable by modelers, but also by experimentalists, with the idea to be portable between simplified models, chamber box models, Plume models, or more complex 3D regional global models, using an object-oriented programming design, and with the main characteristics of having the configuration from all the chemistry as an input to the system through JSON files, with the idea to make the problem much more efficient, to have some kind of solution that scales easily with the chemical complexity, and also to try to take advantage of new HPC architecture, for instance, thinking on the GPUs. So today I will give you an introduction of the concept of CAMP and show you some results that we are obtaining with the system. So the concept that we propose with CAM is to solve all the chemistry, so to create an interface between a host model that provides information on the model state. That can be environmental variables, temperature, pressure, humidity, and also information on emissions, deposition, photolysis. And through that interface, using CAMP as an external library, that the main aim of the tool is to solve all the main chemistry involved on gas phase and condensed phase chemistry. So CAMP is as I mentioned, is being configured through external files. So the idea is that the user doesn't need to recompile their code to change the complexity of a specific chemistry. And it's been developed as part of the PartMC science library, developed and maintained by Nicole Rimmer and Matt West in the University of Illinois. And it also employs external solvers for the ODI system. So one of the first steps to make the system flexible is proposing a way to configure all the chemistry in a way that is easy to implement in models and also easy to ingest in a complex chemistry system. So for that, we decided to use JSON files, where is a nice environment, is a nice protocol to and well fitted to explain and include specific details on the chemistry and types of reactions that a user may be interested to solve. So we have proposed a protocol, a method to explain simple reactions, to describe simple reactions in the JSON files, also to explain also more complex models like unified activity models. And the idea is that the user just put information from papers and literature directly to the JSON files, and then just with these configuration files, you just run your model. So a little bit more details on the internal structure of the concept. The tool is constructed based on object-oriented model design. There are 3 types of abstract classes. So we have reactions, submodels, and aerosol representations. And the way of how the model interacts with any of those classes is always the same. So it permits rapid development of new reaction types, addition of new submodels, and deployment of the system in different host models. So for instance, we have some already in the system, different types of reactions, Arrhenius, Troye, simple base phase transfer, also emission, photolysis, first order loss reactions, and more, and also submodels, for instance, PD5 for inorganic activity and unified for organic activity. And one of the key points of the main of the system, or one of the main goals of the system, is to be able to deal with different aerosol representations. So yeah, we know that it's a challenge to solve the chemistry in different in the aerosol phase. So because this is the solution implemented in models is often tightly tied to the aerosol representation selected by the host model. Nevertheless, the chemistry doesn't really care about that, and as long as some basic questions can be answered from the host model, no? So what's the effective radius of the particles, the number concentration? So in this sense, CAM tries to provide a solution for that, so the user can select different aerosol representations, so model, bin, or particle result. And through the configuration files, where you specify which type or aerosol representation you want to use, the package distributes information in a way that it creates a state with the information of the gas phase species and the different information on the aerosol side. No, so for instance, you have here an example of a model scheme, where you have different modes for one specific mode for black carbon, another for organics, another for inorganics. this can be configured by the user. So it can be completely externally mixed modes or internally mixed modes. The same concept for bin representation. So through the configuration files, the user can define n bins with their aerosol components, and that's all. So you can solve the same chemistry, changing the different representations. And finally, the most complex or detailed representation available in CAM is the one that comes from Part MC, the particle resolve approach, where you model individual particles and their life cycle and how they evolve through time. So some results with representation assumptions. So here you can see we used in a box model, we solve a gas phase mechanism, the carbon bond 5, and we solve the formation of SOA from isoprene, and with photolysis and emission during the 12 hours of integration, and we ran 24 hours. And in this case, we use 3 types of aerosol representations: the particle resolve 1, a model approach with 3 modes, and the bin approach with 8 bins. So in the images in the left side, you can see how the solution for the gas phase for ozone, and in the center panel for isoprene, and isoprene the products of the 2 products to form the SOA is quite consistent, no matter how you decide to solve the aerosols in a model, a bin, or particle resolve. On your right hand, you have the solution that we get for the different assumptions that we make in the aerosol side. So you can see the size distribution at the end of the integration for the 3 cases: the bin, the model, and the particle resolve. And in this case, it's interesting to see what's the implication of an assumption where we said that for the bin and model, the size distribution parameters doesn't change through time, and which is not the case for the particle resolve approach. So this is just a glance of what is CAMP and what can be do. From the computational point of view, we are also working on the porting to GPUs. So the interesting thing here is that, as this is the concept is that this is a library that is used by the host model. It's easy to port it and take advantage of heterogeneous architectures, no matter if the host model has been ported to GPU or not. It gives to the users the chance to take advantage of new heterogeneous machines and speed up the computation of the chemistry. So the idea is to reorganize the hundreds or thousands of reactions of the mechanisms and all the grid cells and take advantage of the GPUs. So here you have an example of the speedups that we have in some specific cases, where we just create a big system, just grouping the grid cells of an Eulerian model and solving the system at once. So you can see here the speed up. This is respect to a case where we are just iterating grid cell by grid cell and solving the whole system. So blue line is this is already in the CPU, but using this multi-cell concept. The red line is the first step of the porting to the GPUs, where we just port the derivative function computation, and the yellow line is porting the linear solver of the system in the GPU. So we are getting really encouraging results, which yeah, it may be a huge improvement in computational time. So finally, just to close the talk, this is the main concept of CAMP. So from information of different research papers, laboratory experiments, a user can configure input files through this JSON standard. and then just run the model without no need of compilation. And this can be plugged in different host models. So we have plugged this in PartMC and also in our Monarch model, that is an Eulerian 3D chemistry transport model, just coding a specific interface. The last comment is that this is being tested. The CAMP is now being tested in the Musica box model suite that Anchor is developing. So hope you will see good results in the near future. So that's all I would like to explain to you today. Thank you.
Thank you. That's this is very exciting work. It's definitely, it's exactly what we had envisioned for Musica. So it's great to see so much progress already along those lines. So anybody can ask questions in the chat, or you can speak up if you'd like to ask a question now. Take a quick question. Pablo asks, can it deal with aerosol growth already?
In PartMC, this is so CAM mainly deals with the chemistry. So the growth of the particle is not in CAM. So CAM only deals with the gas phase, condensed phase chemistry, and then in the case of PartMC, the growth of the particle is solved there. In other host models, you would need additional package for that.
Okay, maybe you can answer Mary's question in the chat. We should probably move along, or we can come back to it at the end of the session. So our next speaker is Haipeng Lin from Harvard University, and he's going to tell us about the HEMCO emissions component. Good morning, Haipeng.
Good morning or good evening, everyone. And I'm just going to share my screen here. Hello, everyone, and I'm honored to present here the development of HEMCO, the Harmonized Emissions Component, as an online emissions component for CAM-chem and CESM. And I'd like to thank my collaborators from Harvard, MIT, NCAR, and NOAA. So the motivation for the creation of a unified emissions and data tool for CESM came partly from the Musica project. So emissions are a central component in atmospheric chemistry models, and they're at the intersection of science, code, and data, as they involve very large data sets which form emission inventories, and also very complex parameterizations and algorithms that describe state-dependent emissions such as biogenic or other natural source emissions. However, source data comes often in different spatial resolutions, formats, and they may also be the need to scale, mask, and overlay emissions for the simulation. So current workflow in many atmospheric chemistry models requires the pre-processing of files, often with many ad hoc tools for regridding and other tasks like masking. So it's a tedious process and also very computationally and storage intensive for doing so for the entire simulation time series. So a unified emissions data tool would aim to complete all these tasks in an online fashion to eliminate this pre-processing step of creating simulation-specific emission files. It will also allow for the better integration of dynamics and meteorology effects on emissions, and also allow for better sharing of data and reproducibility of the workflow. The Harmonized Emissions Component, HEMCO, is an emissions component developed by Christoph Keller in 2014. It's an online emissions component that unified emissions and data processing for the GeoSChem chemical transport model. HEMCO includes an emissions data library with global and regional inventories and a set of algorithms for the computation of state-dependent emissions, which we refer to as HEMCO extensions. The scaling, masking, and choice of inventories for GeoSChem is as simple as flipping a switch in the configuration file, making sensitivity experiments or day-to-day choice of emission inventories possible without any modification of the data or the model source code. And because HAMCO does the regridding and subsetting of inventories to the target simulation grid, all users of HAMCO can share the same input files, and this allows for the seamless sharing of emissions data and greater reproducibility of model runs. In addition to processing emissions, HAMCO is also used for the GeosChem offline chemical transport model as a generic data broker for all components of the model. It is used for retrieving meteorological fields, boundary conditions, restart files, and other environmental data sets using the same regridding, scaling, and masking functionality available to emission inventories. And here's a quick demo of what a HAMCO configuration file looks like. So the HAMCO configuration file is generally organized into two sections, the data containers and scale factors and masks. Each line in the HAMCO configuration file is an entry, and it represents a separate container of data that can be named or numbered. It specifies the source of the data, which may be just raw numbers, or a netcdf file with the variable name of the netcdf file, the date range, the cycling option, and dimensionality. It indicates the units that the data is being read in and the target model species that it is to pass to the model. If it's a piece of emissions, it has the model species name. Otherwise, it's an asterisk, and it will be saved as a generic data container. The numbers on the far right indicate the category and hierarchy, which indicate how data can overlay or replace each other. So emissions in the same category, we use the higher hierarchy when possible. Different categories are summed together for each individual species. The box here shows the scaling factor and the mask number to apply to this particular entry. And scaling factors are not just used for scaling. They may of course be used for diurnal or seasonal, day of week or day of month scaling, but they are also used for conversion or species partitioning. For example, in CAM-chem, sets alcohols are emitted as 15% methanol and 85% ethanol. So you can use scaling factors to partition the species into the model. Masks are geographical and only apply to the container, so that a particular container may only be effective on a particular region. For example, there's an Asia inventory, but it only applies to the China mask, for example, and you can use the masking feature to do this. As you can see here, using HAMCO configuration files can let different models and mechanisms share the same source data. So there's no need to go through the files for individual schemes and change the configuration file to target the right species, partitioning, choice of inventory, etc. However, while HAMCO is a flexible online emissions component, previous implementations were mainly confined to the GeosChem ecosystem. It operated with certain assumptions about the underlying model environment. So we've re-architectured HAMCO into a 3-layer architecture into a data input layer, the HAMCO core, and the model interface layer. The HAMCO core is shared by all models that use HAMCO, thus allowing for HAMCO to ingest the same data sets and perform the same capabilities in all models interfacing with it, and also allowing for the collaboration from developers of all models to improve the way emissions are calculated or add new features, which would then be propagated into all HAMCO models. The other two parts are model dependent. So different models have their own software conventions for I/O and component coupling. This is why we've abstracted these away from the HAMCO core, so that the HAMCO can be implemented into different models without cluttering the core code. These layers are kind of like travel adapters at both ends of the core, with the data input layer handling I/O, and data input from disk, and the model interface layer to pass data computed by the HAMCO core to the model. And it also receives state information from the model for the computation of state-dependent emissions. Our work after restructuring HAMCO 3.0 was to incorporate it as a part of the CESM model. Apart from fulfilling the Musica vision of component interoperability and multi-scale modeling, another important motivation for restructuring HAMCO was the development of GeosChem as a chemistry option for the CESM model. So GeosChem exclusively uses HAMCO as its emissions component. All emissions are processed online in GeosChem. This is a different architecture versus CAM-chem's pre-processing approach. Thus, the opportunity arose for HAMCO to be integrated not only as part of the new CESM GeoS-Chem model, but also as a part of CESM so that it can also provide online emissions capability to CAM-chem. This goal means that we want to implement HAMCO not as a component inside GeoS-Chem, as GeoS-Chem won't be available all the time. We want to implement HAMCO outside a specific chemistry component so that it can serve emissions to any chemistry option or even generic data to any component within the atmosphere. HAMCO CESM is thus the first new model implementation of the restructured HAMCO 3.0, and it's based on the WACCM ionosphere interface in CAM to create a base environment for HAMCO to live in CESM. This allows HAMCO in CESM to be sort of a mini model, self-contained inside CAM. It operates in a way that it works on its own grid and MPI environment so that it can serve the outside model environment regardless of which grid is being used outside. ESMF is used to regrid to and from the HAMCO grid and the CAM atmospheric grid. Currently, the HAMCO grid itself is a regular latitude-longitude grid. The resolution is defined by the user. The reason that it is rectilinear lat-long is because input data in HAMCO is mostly in rectilinear lat-long, and regridding is easier to write for input that way. But we're, of course, looking to use ESMF to do the regridding so that HAMCO can operate on any ESMF grid. This kind of structure has the unique advantage of being implemented outside chemistry. So HAMCO is also agnostic of the chemical scheme that's being chosen and capable of potentially fitting data to other components of the atmosphere as long as the configuration file is provisioned. So at the defined time steps, HAMCO runs, it checks if data needs to be updated, it performs the input of the data, processes it with the HAMCO core, and exports it to CAM, to the physics buffer so that it can be shared among all components, where the exported emissions fluxes or other environmental data can be retrieved out of the chemistry code for its use. This means that there needs to be some code in the chemical scheme to support retrieving the fluxes computed by HAMCO, as HAMCO doesn't touch the model state directly. So what we've done for CAM-chem is, so model supporting code is slightly different depending on which chemical option is being used. We've implemented full 3D emission support for HAMCO within CAM-chem and CESM GC, so GeoS-Chem. In the CAM-chem source code, we've modified the MOSRF emissions that will replace the surface emission fluxes with the data from HAMCO in the physics buffer. And same for the external forcing to inject the emissions into the upper layers. The caveat is that since the list of species supported for external forcing is in code, if there are inventories in 3D that inject 3D emissions apart from the predefined list of species, the source code has to be edited manually. This is not a big issue, but we'll look into improving the user experience. All data from HAMCO is pulled from the physics buffer, and other data sets may be read. For example, CESM GC includes the capability to read in offline land types for its dry deposition, for example. So here's a quick demo of this working in CAM-chem with HAMCO running at 0.9 by 0.9 degrees, and CAM is running on 0.9 times 1.25 degrees. This is the stats global inventory with the NEI US inventory replacing the global inventory in the US area. These is our surface fluxes of NO with hourly average for 1 day. So this data comes directly from the HAMCO library. So it's the same input source files that are being used in GeoS-Chem. No changes in data files when necessary. Of course, the mapping of input file species to the model species, especially for organic or aerosols, etc., need to be provided in the configuration file. So this essentially moves the pre-processing information into a text file rather than having to distribute different pieces of processed data. So it's easier to reproduce and it saves disk space. Right now, HAMCO CESM works in both CAM-chem and CESM GC. The basic functionality is all working, and support of inventories in CAM-chem is contingent on providing the species mapping, but essentially they can use the same input data. Algorithms for state-dependent emissions, such as dust, sea salt, and volcano, are also being developed. The infrastructure is fully functional. Again, we just need to map the species and also validate that these algorithms are running correctly in the new model. Future directions include, first and foremost, the support of parallel input using the CDEPS data model in HAMCO. Right now it's using serial input, and this is the main hurdle right now. After that, we hope to incorporate HAMCO CESM into the CESM mainstream. We hope to better incorporate HAMCO's unified approach for algorithms and also sharing data across all models using HAMCO in the future. So the goal is to achieve full interoperability of data sets between all models using HAMCO. With this, I'm happy to answer any questions. Thank you.
Thank you. Another development we're very eager to have functional and CAM-chem CESM. Sergio asks, is it possible to input bottom-up emissions inventory into HAMCO?
Hi, Sergio. Yes, well, depending on if you have the netcdf input files, then it is possible to just incorporate it using the HAMCO configuration file. And if it involves any other processing that needs to be done in source code online, then it can be incorporated in the form of HAMCO extensions. So I think that's definitely possible.
Yeah. So in the interest of time, we'll move along. When you ask questions in the chat, please remember to include who you're asking, because it looks like we're going to have a fair amount of discussion. So our next speaker is Tim Butler from IIS at Potsdam. Good evening, Tim. Thank you for joining us.
Yeah, well, thank you for the opportunity to present this work on ozone tagging with toast and CAM-chem. I'm trying to share my screen here. Can you see that now?
Yep, looks great.
Okay, great. So yeah, I've presented various development versions of this work at previous chemistry climate working group meetings, and it's nice to be able to present some real results this time around. So I'd just like to start with a quick introduction to how we do the ozone source attribution with the TOAST module, which stands for Tropospheric Ozone Attribution of Sources with Tagging. And then I'll show an example of that for the year 2010 based on the HTAP framework, the Hemispheric Transport of Air Pollution emissions and region definitions, and then talk about some of the future directions that I'd like to see this work take. So just as a generalized way of looking at VOC oxidation and ozone production, we start with a VOC of any kind. It's oxidized, of course, to something slightly more oxidized. And this can go by multiple steps until ultimately you end up with CO2. At most of these steps along the way, you can convert a molecule of NO into NO2, which is basically the fundamental process that produces the tropospheric ozone through the subsequent photolysis of this NO2. And this can happen, of course, at multiple steps along the oxidation chain of these VOCs. And so we've basically hijacked into this process the necessary code and logic to do the ozone source attribution to either VOCs or NOx as precursors of ozone. So how that looks for a VOC precursor, for example, let's just take a biogenic VOC, which we'll put a label on. We'll call that VOC bio. And then through the oxidation chain, we'll basically retain that label in all of the products of each of the reactions as a new tracer in the model and a bunch of new reactions in the chemical mechanism to keep track of which intermediate VOC comes from these biogenic VOC precursors. And then when we have an NO to NO2 conversion in any of these reactions, the NO2 can inherit that label, and then so the ozone subsequently also inherits that label for all of the steps along the way. And if we do that for all of the different classes of VOC in which we're interested, then we can do a complete attribution of ozone to the VOC precursors. So we can also do that for NOx. We do that separately to the VOC attribution. And here we have our chain again of VOC oxidation. We have, for example, an NO from an anthropogenic source coming along to one of these points in the VOC oxidation chain. This gives us an ozone from anthropogenic sources. And we might have a biogenic NO molecule from soil emissions, for example, coming in at another one of these stages of the oxidation chain. And so by keeping track of the emitted NO precursors, we can then follow this through the the chemistry all the way to attribute the ozone that we ultimately produce back to the precursors which were emitted. And so we can do this for both VOC and NOx. We've done this. And so we've done this for the HTAP, hemispheric transport of air pollution source regions. So we've basically labeled all of the anthropogenic NOx and VOC precursors from each of these source regions on the left, and then looked at the resulting ozone concentrations in the receptor regions on the right. And then we can do that, we can do a complete ozone source attribution based on this. So here are some details of how we've done that. We've used 2010 emissions from the HTAP multi-model study. Like I mentioned, we do 2 runs, one for NOx and one for VOC to do these attributions separately. We use quite an old version of CAM-chem because this is the version that we started implementing this system in, and it takes quite a bit of implementation work to do this. So we're kind of stuck in this version at the moment. We run at about 2 by 2 degrees, which is needed because the tagging does get fairly expensive if you have a lot of tags for your ozone. And we use specified dynamics from the GEOS 5 analysis product. So there are 2 papers which you might be interested in here. The first one is a GMD paper from 3 years ago now, which talks about the technical implementation details of this system. And in the supplement to that, we provide all of the modified source code files for this version of CAM-chem, as well as the helper scripts that are needed to basically rewrite the chemical mechanism and parts of the model to be able to work with these dynamic sets of ozone tags that we introduce. And much more recently, in September last year, we published a paper in ACP actually using this system to do an ozone source attribution for these source and receptor regions. And so here's a taste of how that looks. So this is our attribution of surface ozone as an annual average in 2010 to the NOx precursor emissions. And so this is our total simulated ozone, and here are also a selection of different ozone from these different precursor emissions. So we see, for example, the ozone due to NOx from lightning. We see the 3 major anthropogenic source regions in the bottom here, and oceanic sources is basically shipping. And so you can see, of course, that in each of these anthropogenic terrestrial source regions, that the ozone from the NOx emissions there is primarily concentrated over the source regions. But then you also have this footprint which extends into the background of the northern hemisphere as well. And quite a lot of ozone from NOx from shipping, concentrated mostly over the ocean basins and the shipping routes, but also coming into the continents and especially near the coastal regions. We can also do this for VOCs. So this is a second model run with the VOC tagging instead of the NOx tagging. Our total surface ozone is the same because we use the same everything else, but we attribute ozone differently this time to the VOC precursors. And you can see a huge role, of course, for methane as an ozone precursor and biogenic VOC, primarily isoprene in the annual average contribution to 2010 ozone here. And then you see, compared with the NOx tagging, the VOC, the anthropogenic VOC, plays a relatively smaller role compared with the biogenic VOCs and methane. But interestingly, for East Asia, we see a much stronger signature from the anthropogenic VOC from East Asia than from the other major anthropogenic source regions. So there's a lot more I could show there, but I think I'll just give you, in the interest of time, I think skipping on to some of the other results is useful here. So we can look at the seasonal cycles of a monthly mean surface ozone. This is for the Northwest United States receptor region from this HTAP region definition. And here are basically the 2 runs shown side by side. So the NOx tagged run and the VOC tagged run. We see in black here the total surface ozone in this receptor region, northwestern United States. Between the NOx tagged run and the VOC tagged run, the ozone is identical by design, but we do the attribution differently. On the left, the ozone is attributed primarily or purely to NOx precursors, and on the right, purely to the VOC precursors. And we can see some interesting patterns. So we see the local NOx emissions are here in green. We see the peak in summer to the ozone from the local NOx, and transported ozone from remote sources here in pink. And so we see that the springtime peak has a large contribution from ozone transported from other anthropogenic source regions. So the stratosphere is down here in blue. So we see, of course, a strong springtime signal in stratospheric ozone, but the transported ozone from remote source regions is making a larger contribution in this region at this time. And we can break that transported ozone down much further into its component parts of where the NOx was emitted that got transported into the northwestern United States. And we see, of course, as you might expect, the signal from East Asian NOx emissions has a peak in spring. But actually in CAM-chem, the way we do this, we see a much stronger contribution from shipping. That's the oceanic source. So we can see a very, very strong role for ship NOx in springtime ozone. And we see a similar pattern in other receptor regions as well, especially on the western coasts of the continents. If we look at the VOC tagging, then we see a similar picture. We see, let's start with the main contributions. We see a year-round contribution from methane. We see a peak in summer from biogenic VOCs, and we see a relatively small contribution, that's the pink here, from the transported species. And we see here quite a strong peak in the East Asian contribution to ozone. So how does the model run compare with observations? And we've compared our simulation to the TOR observations from 2010 for this region, and as well as the model ensemble from the HTAP multi-model exercise. So the TOR observations are here in black, and the model range is here in this gray sleeve here. We can see that all of the models generally overestimate ozone, which is a fairly well-known problem with these models. And we can see our model here in blue, which is also behaving like the other models of overestimating ozone. So we can see the TOR observations have the springtime peak, but not so much the summertime peak. So this blue line for the tagged CAM-chem model is an outlier here in this case. And we can see here that this summertime peak is to a large extent driven by biogenics. So if we want to understand why there's this summertime peak that isn't seen in the observations, then we can start to look at the biogenic emissions. We don't just tag ozone with this system. We can also tag every intermediate species that's generated through the chemical mechanism. So here's an example of PAN, which has both a VOC part and a NOx part. So we can show the PAN from our NOx tag simulation and from our VOC tag simulation in the lower troposphere here between 800 and 500 hectopascals, I think that is. And we see a springtime maximum in PAN as we'd expect. We see a large contribution in the springtime maximum from the transported component over Northwest Europe. And we see something very interesting here. So if we look at the VOC part of the PAN, we can see, as you'd expect, the contribution from the North American VOC emissions, since it's immediately upwind of Europe, but also quite a strong contribution from East Asia. So this is, of course, much further upwind, but it's also still making quite a strong contribution. But then if we look at where the NOx part of the PAN is coming from, we see that this is in both cases for North America and East Asia is less than the VOC contribution to the PAN, or the contribution of these regions to the VOC part of the PAN, and that the missing contribution for NOx comes from basically ship NOx emissions. So I might have thought that if we looked at a PAN from these different source regions, that the PAN might have actually been formed in the planetary boundary layer of the polluted source regions in each case for North America and East Asia. But it seems that in CAM-chem here, in this simulation, a lot of the PAN is being formed downwind of the major source regions within a strong input from ship NOx. So it gives us a window into what's going on with not just the ozone, but also with the intermediate chemistry as well. So we can also look at the overall ozone production potential of the entire Northern Hemisphere, which we've taken as a proxy for that. We've taken the modeled OH reactivity from VOCs, which is often used as a way to understand ozone production potential. We can see year round that this remains really quite constant, actually, the ozone production potential of the air in the Northern Hemisphere, but that over the course of the year, the contributions to this reactivity change quite a lot. So we see a strong contribution from methane all year round. we see in the biogenic contribution to the VOC reactivity that, that there's a peak in summer, as you'd expect. And for the anthropogenic component, we see the opposite signal, the opposite phase to the biogenic VOCs. So we see a maximum in winter and spring and a minimum in summer. And then of course we can break this down into the individual components of the anthropogenic VOCs, and we see a strong role for East Asia. And what seems to be happening here is that when the lifetime of the VOCs is short in summer, the contribution to the ozone production potential is small. But then as the lifetime of these VOCs gets longer over the course of the winter and the spring, they tend to build up in the Northern Hemisphere and give us a large amount of potential to produce ozone in the spring when the photochemistry starts again, then giving us this springtime peak in ozone. So we can start to understand where this springtime peak in the ozone that we see in CAM-chem and other models is coming from. So what are the next steps? Well, we'd like to implement this in Musica, of course, so we get the benefit of this state-of-the-art model, and so that we can continue to make this system available to the public. But in the meantime, we're also going to continue working with the version we have in CESM 122 because it's working and it's producing interesting results. So we would like to do a transient run now. We showed 2010 just earlier. We'd like to run 2000 to 2018 to get an idea of the contribution of different sources to the trends in tropospheric ozone. So to do this, we're using the CAM's global surface emissions. We're using the CAM's shipping emissions. We're getting a higher resolution on our shipping, so we're tagging the shipping emissions by ocean basin and the emission control areas around North America and Europe. We're using a time-dependent surface methane concentration from the CAM's analysis, and we're currently looking for a good specified dynamics data set, and I'll get onto that now in the test runs that we've seen, that we've done so far. So here's an example of test runs from 2004 till 2018, looking at the background ozone import into Europe by way of the Macehead observations. So that Macehead data from the TOR database are here in the black line. We have our long-term run of CAM-chem with the GEOS5 analysis product. We see it was doing quite well up until around about 2013 or so, at which point the performance gets a lot worse, which seems to me likely to be due to some kind of change in the analysis system used in this product. So we've tried to use the MERA2 reanalysis, but we see significantly worse performance for the background ozone here. We haven't done the entire period, we've only done a few years. This is potentially related to the version of the GEOS5 model used to produce the MERA reanalysis. So we currently don't know exactly how to deal with this and what what specified dynamics data set to use in order to get a reasonable agreement between model and observations. That's an open question. We've looked into this a little bit more and what the causes of this sudden jump in the background ozone might be in our GEOS5 simulation, and we can see that the vertical structure of the ozone in the troposphere is changing significantly here. So around about 2013, we start to see a lot more vertical mixing. So we're seeing more probably stratospheric ozone coming down into the surface in this later period, which is quite possibly what's also happening with the MERA2 when we use the MERA2 specified dynamics. So just to summarize, this system works, the tropospheric ozone attribution of sources with tagging, and we can do all sorts of attribution of things in the atmosphere to NOx and VOC precursor emissions. We would like to implement this in Musica, but we're using CESM 122 in parallel to that to do HTAP related work, especially with the attribution of trends in surface ozone. I think will be very interesting, but we currently have this problem of overestimating the background ozone, especially in the winter and spring. And so it would be great to hear if the group here has any suggestions for how we might be able to overcome that. Thank you.
Great, thanks, Tim. In immediate response to your nudging problem, you might want to try the physics-based nudging that we're offering as a comp set in CESM 2.2, but it's just name list options. So you could use that in CAM4, I think, as well, instead of specified dynamics. And that's using the meteorology on the model levels. And so that might alleviate some of the strat-trope exchange problems you've seen.
We'll look into that. Thank you.
So we can help you with that. Does anyone else have a question? I can't see everybody, so speak up if anyone wants to say something. No? Steve. Hi, Steve. Tim asked Tim, have you looked how the PAN tags are related to the efficiency of vertical export from the different regions? How does this compare with chemical or precursor differences?
We haven't looked in any great detail at that, but that's certainly something we could do with this. I think we've just scratched the surface of what we can do with this system so far, and there's a lot more to be done.
Yeah, these are really exciting results. Look forward to looking at them more. If people have more questions, add them to the chat and Tim can answer as we move on to the next talk, which is by Rafa Fernandez on the current status of VSL halogen chemistry in CESM 2.2. Rafa, are you there? I can see your name.
Hello?
Oh, there you are, at second place. Yeah?
Yeah, sorry.
Oh, a third? Yeah, okay.
So, sorry, I just got disconnected for a few seconds, so I just share my screen now.
I know how that goes. Looks great.
Looks great, okay. So, first of all, thank you for the opportunity to speak on this nice working meeting. My name is Rafael Fernandez from the National Research Council in Argentina, and I'm presenting the current status of very short-lived halogen chemistry in CESM 2.2. This is a project led by Alfonso Saiz Lopez in Madrid. I was a postdoc there a few years ago, and this is all the people from CSIC and also from NCAR helping us with this implementation. So basically, I will present a mostly technical description of how we implemented all this halogen chemistry in CAM-chem. I will focus mostly on the processes and reactions we implemented in the model more than in the impacts or implications, and also highlighting the main chemical reactions, routines, and name disruptions that we needed to change for the non-very short-lived CAM-chem users, so they get familiar with this. Just to highlight that all of the development we have published in the recent years have been performed with CESM 1, and we have, during last year, worked on the porting of all this chemistry into CESM 2, and we found out some quite interesting differences that we have mostly solved all already. And just to focus with some of the implications of using a simplified versus a full halogen approach in the troposphere. So basically, this is from WMO 2018. So when ozone-depleting substances are emitted from the surface and transported to the stratosphere, they are changing from source gases into reactive product gases, and many processes affect all this transport. We will focus mostly on heterogeneous reactions, which involve sea salt recycling, which acts as a net source of halogens to the troposphere. Also, the washout and scavenging of soluble halogen species in the free troposphere to end up talking about some heterogeneous recycling on ice crystals and sulfate particles that change the partitioning among reactive and reservoir species. So this is the first point about emissions. So there is a setup of a CAM-chem setup for CCMI. I think it was the tag version CCMI 34 that included some lower boundary conditions of bromoform and dibromomethane. They were included with a special interest of addressing a complete total stratospheric bromine levels. So these lower boundary conditions were not included to represent properly halogen impact in the troposphere. So in our very short-lived scheme in CAM-chem, we do not use, we get rid of these lower boundary conditions in the name list, and we include a set of different emissions files. These are netcdf files that has a spatial and seasonal distribution, which is quite variable and depend on chlorophyll A satellite maps. And within those emissions included in the name list file, we get a quite reasonable representation of these source gases, brominated source gases, respect to some both oceanic ship measurements, and also some aircraft measurements of major very short-lived species, which are here the blue and the yellowish lines, and also for the minor very short-lived species, which also contribute to the total bromine.
Oops, guess we lost him again. Maybe wait a minute, see if he comes back.
Maybe we should move on and see if he comes back later.
I have his slides. I don't know if anyone wants to online can jump into.
He may be back.
Talk about them. Okay, well, oh, there you are.
So I'm back.
You're back.
Yeah, sorry about that. Not sorry until which stage did you get, if I still have time?
Let's see, I'm looking at your presentation. I don't know, I think you were only on about slide 8. Yeah. Yeah,
okay,
there. Right.
Shall I continue from here?
Sure, yeah.
Okay, so we implemented an iodine emission, inorganic iodine emission on the model, considering based on laboratory and also some field experiments based on the ozone deposition on the ocean surface and the reaction, the oxidative reactions with aqueous iodide at the ocean surface, and the subsequent release of molecular iodine. So in CESM 1, we have everything implemented in more SRF emissions routine, and we always set this original mean. We included an external file just to keep track of these two species within the surface flux array. But then we needed to force them to 0 to compute all this online. When we shift into CESM 2, somehow this set to 0 emission was not implemented in this emission. And we are getting almost twice the original flux because we were considering the initial emissions from the input file, but also the online emissions. that was something that we have already fixed. And when we've been able to reproduce the total results that we had in CESM 1. The important point here is that iodine chemistry in the troposphere can represent almost up to 30% of the total ozone destruction, at least within the tropics, as we have computed in previous studies. So in addition to the source emissions, we also talk about sea salt recycling. So these are non-stoichiometric reactions implemented in the chemical scheme, which a gas phase halide reservoir species interacts with the sea salt and uptakes bromide, or chloride from the aerosol bulk, and then is released again to the gas phase. So this process is very non-linear, and it represents a net source for bromine and for chlorine. But for the case of iodine, it only represents just a change in partitioning. So there is not a net source of iodine, but just for bromine and chlorine. This process basically follows the free regime approximation. And so we need to derive the reaction coefficient, or the gamma coefficient, and also the surface area density of all these, the fields where all these reactions occur. So basically implementing these reactions, we noticed that the total topophotic bromine, so this is the difference between a simulation without considering a full approach in the troposphere and considering our full approach, the difference in the bromine loading. So we get up to 2 times larger bromine species below 500 hectopascals, average within the tropics. But even when in the lower troposphere we have larger bromine loading, then in the free troposphere we end up having, with the full scheme, smaller values, smaller mixing ratios comparing to a standard simulation. And that's because our scheme, in addition to this recycling of sea salt, also includes washout and ice scavenging, as I will explain in a few slides later. So just to highlight some of the differences between CESM 1 and CESM 2. So tropospheric sea salt aerosol is up to between 5 and sometimes 8 times larger values in CESM 2 than in CESM 1. So as these recycling reactions are non-stoichiometric and are sometimes quite explosive, this affected a lot the surface levels of bromine in particular. So we needed to tune basically the gammas, and we got different approaches to reduce also the surface area density among these 2 model versions. And we found 2 different approaches, and both of them worked quite well. One was implementing a cap on the total surface area density, and the other one was for sure to reduce the efficiency of these gamma reactions. So, but basically, this is again comparing CESM 1 and CESM 2 on the right. We reproduce the total tropospheric BRO column. This is latitude versus day of the year in the x-axis. So we kind of completely reproduce the seasonal behavior, just with a small difference that in CESM 2, surface levels are a bit higher, and then in the free troposphere, surface levels of BRO are a little bit smaller in comparison to what we were having in CESM 1. So going into what I told you of this washout on liquid clouds, so I will explain this with the implementation for iodine. So CAM-chem basically used the NEU routine for implementing the wet deposition. And we found out that for the case of iodine, which most of these species are very soluble, so the efficiency of washout following NEU routine within the gas wet depth list, and also we implemented an ice uptake list into the structure of the code. The washout was so efficient that we were almost removing all the iodine atoms that were released above 5 kilometers. So we turn it off, all this washout for this species, because all the halogen implementation include washouts for independent and individual species. And we implemented also a free regime approximation where we remove one atom of iodine for either HOE or iodine nitrate, also for the within the free troposphere, and based on these liquid and ice SAT fields. And with this, we were able to reproduce measurements of both iodine and bromine. So going into the change of partitioning reactions that we implemented, the CAM-chem and WACCM has a very complete stratospheric halogen chemistry mechanism. So we took that mechanism occurring on the stratosphere in sulfate aerosols and also on ice crystals, and implemented equivalent reactions also in the troposphere based on instead of using stratospheric SAT fields, we implemented those reactions on tropospheric ice, which are quite important basically within the tropical tropopause layer. And within those reactions being active, we avoided to increase too much the concentration of reservoir species and to move them into reactive species. And with this, we were able also to change the efficiency of washout and being able to reproduce on this figure on the bottom. We see these empty circles and pink and blue lines going increasing. These are the total inorganic bromine being transported to the stratosphere. And we get to see and to compare with the best assessed report in the last WMO report of the source gas injection and product gas injection of these short-lived species. Equivalent processes of these change partitioning reactions were also implemented for iodine chemistry, because like similarly, if we don't include these reactivation processes, which are not a source, but just a change of partitioning, we were not able to reproduce measurements of IO in the free troposphere. And based on our modeling studies and the comparison with measurement, we suggested the possible contribution of inorganic iodine also to a stratospheric injection. So there could be a role of iodine in ozone destruction in the lower stratosphere. And this has been taken also within the last WMO report. And finally, this last year, this injection of iodine to the stratosphere, if it's somehow occurring as we are modeling in our model, we found out based on some iodine content on aerosols in the free troposphere and lower stratosphere, we find out that we know that iodine is playing a role on new particle formation. So we implemented a very, very simple approach of just changing, considering that a fraction of the reactions that are being recycling on crystals or sulfate aerosols can be also being uptake for those within those aerosols and being transported as particulate iodine to the stratosphere. And we were also very capable of reproducing observation of both gas phase iodine and also aerosol iodine content within the mid-latitudes, the northern hemisphere mid-latitudes where the measurements were performed. So basically this is it. This is not a really beautiful slide, but just to show on top, these are the SAT fields for CESM1 and in the bottom for CESM2. So on black, this is sea salt. We see changes of almost 1 order of magnitude between the two models, and that makes a lot of noise in the recycling of sea salt recycling. There are also some large changes, mostly on liquid content in liquid clouds between CESM1 and CESM2. And I would like also to highlight that this is also the case when running the model in a free running configuration or a specified dynamics configuration, where the clouds are resolved in a different way. And this is also affect washout. And finally, there are changes in sulfate SAT, depending if we are using prescribed fields or not, that can also impact on the total halogen loading in the TTL and in the transition to the stratosphere. So this is it. Basically, now we have included all the halogen chemistry in CESM 2. Most of the result published until now has been based on CESM 1. So basically our approach has been to reproduce the levels that we have in CESM 1 with the latest version of the model. We needed to get rid of some deposition or washout processes using the Nell routine and to implement the free regime approximation to reproduce these results. And we would like to highlight finally the importance of having a proper representation of a full chemical treatment of halogens in the troposphere and stratosphere with CAM-chem and also with WACCM, because it's not computational too much expensive and results are much in agreement with observations. So thank you very much.
Thank you, Rafa. That was great. This is impressive amount of work you've had to do to get this all working. You've touched a lot of different parts of the model to get this working. Simone had one quick question in the chat asking if you use the new aerosol convective wet scavenging approach. So if you use the default CAM-chem, then that should have been turned on.
Yes. We follow some instruction from Doug Kinison and also from Simone of the best standard implementation, and we are using that final approach. I think that's one of the reasons the aerosol in the lower troposphere are different.
Yeah, I don't remember. Sorry for the question, but I wasn't sure if we added that because in the later CSM 2.2 version, there are changes. And so I wasn't sure if I had mentioned. Maybe we should check just to be sure.
Okay, sure. We can check it for sure. That would be great.
Good. Well, thank you. Look forward to using that version of the model for various studies. Let's move on to our next speaker, who is Ben Gobert from NCAR-ACOM. And he's going to tell us about his recent simulations looking at the impact of COVID-19 lockdown.
Hi, everybody. Can you hear me?
Yep, can hear you. And presentation mode, perfect.
All right, so yeah, I'd like to thank all of the co-authors who participated in this study. It's more like a collaborative work with labs in Europe and Asia on top of the US. So everybody knows that there was a series of lockdowns that induced a large reduction in anthropogenic emissions, and that's a really interesting study for quantifying the impact of the emission reductions. But the emissions were varied by sectors. They lead to different variation according to the pollutant, according to the respective sectors. And it's not that easy to model since you can only use proxy to estimate the emission reduction. It also varies by country, states with different timing, and also happens at different seasons, which leads to different concentration response according to the season, and so the chemical regimes, the weather patterns, and other things. So here's an example from the Forster et al., who was like the first emission estimate for reactive gases, and they show quite a large spread between emission estimates of the COVID reduction. So here we adopt the conform inventory. They also used proxies of activity to estimate daily adjustment factors at 0.1 degree globally. So it's the second global estimate of reactive gases emissions. they considered road transportation industry, power, residential, shipping and aviation, and developed adjustment factors for each of the sectors. Then we applied those sectors to the CAMs, global inventory that includes the MEG emissions over China. So that's interpolated to 2020, and then we did first daily emissions from the monthly emissions and then applied the daily adjustment factors. So when you put that at 1 by 1 degree in CAM-chem, you get something like this, where in February it's mostly lockdown over China, and then in April it's lockdown in many places of the world, but maybe not so much in China anymore. 40% for NOx and 25% for VOCs in China, which is quite significant. And yeah, overall the reduction are up to 50% according to those estimates. So then when you put that in the model with also 2020 fire emissions, so daily emissions from QFED with tropospheric and stratospheric chemistry and the latest CESM 2.2. We also use MERA2, also because I want to look at then a 20 years average. So I want a consistent meteorological inputs, because the geosphere had jumps for some years with the different versions of the models. And we apply quite a strong nudging of 6 hours relaxation time for U, V, and T to reproduce the weather of 2020. And then you can have an estimate of the NOx concentration, this time reduction, that are usually much smaller and varies quite a lot in space also. So then starting to look things into more details and put that in relation to the previous years and what is the impact of dynamic versus the impact of emission reduction. And so for instance, in Europe, we see quite an increase of ozone in the north and quite a decrease in the south by having just the emission reduction. But if you look at, if you compare this with a 5 years average pseudo climatology with constant emissions, you can see that the impact of the weather patterns during the European lockdown, so this is the map for April, are actually larger than the actual emission reduction. But only both of them combined can be seen from the observations, and you can see that it's actually, the model is actually reproducing those changes really well, actually. Another things we know from the observations is that there has been a reduction in the free tropospheric ozone by around 7% from the ozone zones and NDAC global networks. And so there is, the 7% is mostly in the northern hemisphere, with a peak in April and July that are significantly different than the 20 years average. So we wanted to see how well CAM-chem is reproducing those trends. And so here are the differences between COVID emissions reduction and the control for 2020, the combined effect for NOx, surface only and aircraft only. And you can see that in the northern hemisphere, free troposphere, the actual reduction in NOx is dominated by aircraft that were quite low in late spring, summer. And otherwise you have quite significant decrease towards the surface that can be pushed in the upper atmosphere if the dynamic allows it. And when you look at the impact of ozone, you can see that we found a decrease of around 7%, which is in line with the observations. And that the decrease in ozone is half aircraft, half surface with a bit larger weight from 4% reduction just due to the aircraft. So it's quite significant. So the aircraft emissions are dominating the reduction in the Northern Hemisphere spring ozone reduction. But the other thing that struck me was the fact that the stratospheric ozone was also quite low, and the timing is also pretty much the same. March and April, really low stratospheric ozone in the stratospheric or Arctic ozone. But so we're not that interested in the change in ozone here. It's just a CAM-chem simulation. But the impact on the stratospheric ozone on the free troposphere can be significant, knowing that most of the ozone in the spring is from the stratosphere. So we actually did a difference between April 2020 ozone versus a climatology, which is now 2001 to 2011. So for ozone and for our own made stratospheric ozone tag, and you can see that there is a large reduction in ozone, and that we just saw. So it's not just the emissions, but also with regard to the climatology, as shown by the observations, but also an anomaly in stratospheric ozone down to the surface. So, I mean, quite a large impact for the Northern Hemisphere spring. So this is still a work in progress on the stratospheric ozone. I also did evaluate the emissions using CAM-chem DART to assimilate MOPIT CO for the Chinese lockdown. And I did compare with the different estimate of the emission reduction. And you can see that, so the red is the one we are using, which is reduction by around 15% net for CO, knowing that there are compensation between the different sectors. And you can see in blue that the estimate from Forster is much larger, in relatively speaking, with also a different shape. And the purple is when I'm using the simulation of MOPIT to constrain the red line. And you can see that it's a larger, steeper decrease, but also a larger increase after the reopening, after the vacation / lockdown of the Chinese New Year holidays. And so there are some differences in the estimate of the emission reduction, but the MOPIT inversion is actually not that different from the prior in terms of relative change due to lockdown, compared to usual inversions where you can have quite large errors in even CO emissions that are not the most uncertain sources. So to conclude, CAM-chem reproduces the observed ozone feature with quite a great accuracy. There is more work to be done on the absolute values. There may be some biases that were noticed and kind of known, but it looks like the variability is well reproduced. The free tropospheric ozone is also really well reproduced, where half is due to aircraft and other half from the combined effect of the surface lockdown, with probably a role of stratospheric ozone in this change with regard to the long-term mean of ozone. And so the uncertainties in emission reduction can be large, but not larger than the actual emission inventory emissions. So for future work, I think it would be great to use the Musica to be able to take full advantage of the fact that we're using now 0.1 degree emissions. That is also true for biomass burning, especially that 2020 was also great for fire emissions, where completely dominated the anthropogenic emissions in some places like the US, Western US, for instance. And also looking at heterogeneous chemistry by constraining CO and AOD to improve the PM and look at the PM impact on ozone, but also just PM emissions and concentrations. So that's what I have.
Great, thank you. Ben, are there any questions? I don't see any in the chat, so if you have a question, speak up. Nature certainly didn't make this COVID atmospheric experiment very easy. Stratosphere, fires.
I don't see anything.
No? Okay. If anyone has any further questions, please put them in the chat. And we will move along to the next talk by Forrest Lacey. We're now moving into the Musica section of the session. Several talks on our new Musica version 0 configuration.
Hi, can everybody hear me okay?
Yes.
Okay, let me just share the screen.
And so Forrest will be talking about evaluation of CESM as a tool for health impact modeling of ambient air pollution. He's also at NCAR in ACOM and RAL.
Okay. Okay, can you see that?
Yep. Looks good.
Had to change permissions for some reason. I'm going to talk to you a little bit about some of the simulations that we've been doing as part of the Musica version 0 validation. And first I wanted to just give a little bit of motivation, which has really been at the forefront of the last year of 2020. Just within 2020, we had a number of different cases that have highlighted the need for a global model that is capable of estimating ambient air quality at exposure relevant scales. So historic wildfire seasons, extreme weather events, such as the tropical cyclones and hurricanes that we saw. And then also COVID-19 driven emissions changes that then can be transported to other regions. All of these really drive the need for a global model that is capable of estimating exposure level concentrations. So just as a little bit of background, because I'll be talking about my results in terms of this, is defining population weighted PM 2.5. So what you're seeing here is the Musica version 0 results aggregated to a 1 degree grid and then to close to the native resolution of 1/8 of a degree. So that's what each of the different grid boxes are. So this is the same simulation. I've just aggregated it to 2 different scales. And now you can see here, if I look just at this box that contains 4, it's basically a 2 degree by 2 degree box. We have 4 grid cells if you aggregate it to 1 degree, whereas you have many more than that if you put it at the 1/8 degree. And so what population weighted PM 2.5 is, which is the metric that's used for exposure estimates and health calculations, is if you take the population in that same area, you pull out your concentration, and then you multiply that by the population within that area at the subgrid scale, and then you divide by the population within your entire domain. So if we're considering this 2 by 2 degree grid, that would be the total population within the gray box. And that's equal to the population weighted PM 2.5 for that specific region. And you can quickly see that even just aggregating the same results to different scales, we do get a change in population weighted PM 2.5, and this is scale dependent. So for these 2 specific cases, this is just a snapshot over Washington. With 1 degree aggregation, we're getting 4.4 micrograms per meter cubed. where we get 4.51 micrograms per meter cubed, or about a 3% difference. And this is on the smaller side. They can be much larger than this, and they especially differ if you have different grids representing the model calculations. So in order to investigate this, we started with Musica version 0, which is basically CESM 2.2 using the SE die core and regional refinement. And we looked at modeling the formation and fate of different pollutants, and also using both different resolutions and also using different mechanisms. So if we wanted to investigate horizontal scale, we did the 1 degree cube sphere, which is the NE30 grid. And then we also did the global 1 degree with 8th degree grid cells over the US, which is the NE0 CONUS 30 by 8 grid. So that basically denotes that it's a 1 degree global grid with 8 times magnification in your area of interest. And so the grids are shown here. And I've also overlaid the EPA region outlines because that's what I'm going to be discussing the results as. We also were interested in chemical complexity. So we tested both with the standard Mozart TS1 mechanism, along with the Mozart TS2 mechanism that has improved isoprene and terpene chemistry and adds around 80 species and the corresponding chemical mechanisms. So the question that we had is, how do these changes impact estimates of ambient air quality and the resulting health impacts? So here, this is just showing a sample of the contributions to population-weighted PM 2.5 for each grid cell over the US at 0.1 degrees. And this is a log scale, and really what you're seeing is population distributions. But this is just kind of a visualization of where in the US population-weighted PM 2.5 has the largest contributions. So you see in general, population centers have the largest concentrations, but you also see more persistent particulate matter concentrations in the eastern US versus the western US. And I wanted to show a couple cases where both resolution has a large amount of significance, and then also where chemical complexity has significance. So one case that is very interesting to me, and I think important to the community in general, is wildfires and other localized sources are becoming more important with respect to ambient air quality. There's been a number of studies, and there will be more studies focused on the long-range transport of wildfire pollutants and how those impact health. And so what I'm going to show here is the difference in how the 1 degree model represents the rim fire, which was in California in the second half of 2013, how the 1 degree model represents that, and how Musica version 0 represents that. And you'll really get an idea of what that means for health impacts. So here, what you're seeing around the middle of this video is the rimfire starts. And you see on the left panel, very discrete points that are defined by the burned area, and they're persistent. Whereas with the 1 degree model, they are mixed throughout a much larger area. So the 1 degree grid cells are around 100 by 100 kilometers. So you really get some mixing of that. And then that is shown in the absolute difference, where you have underestimates of pollutants in the region local to the fire, but then overestimation of pollutant concentrations for a large region outside the fire that could potentially include population centers. And the scales here are going from 0 to 50 micrograms per meter cubed, and then 24 to negative 24 on the difference plots. So this is really showing that resolution matters when it comes to things like point sources or localized emission events. Now, when we're interested in chemical complexity, we can see some different behavior. And this I've again taken kind of over Southern California, where we have the Mozart TS1 mechanism on the far left In the middle is the TS2 mechanism, and then the absolute difference, this is again running through August of 2013, is shown on the right. And what we start to see here is we see very similar patterns, which makes sense because this is both using the same die core on the same grid. But we do have changes of up to 30 ppb in what the ozone concentrations are, specifically in outflow from the Southern California basin. So again, this is showing purely the impacts of chemical complexity on on health relevant pollutants. So this is just another case showing where your choices of model complexity really matter when you're looking at the health relevant pollutants. So the way that we've tried to aggregate these results is, as I showed earlier, we have the EPA regions 1 through 10 that kind of go from east to west. And the first thing that I did was to compare the model results to observations from the EPA AQS sites in those regions. And that's what's being shown here. And in general, what we see is a model high bias that if we're looking at ozone, we have a model high bias, which we expect based on how CAM-chem represents ozone. But the largest improvement in that bias is for resolution, is for populated areas based on resolution, and then in the summertime for the chemical mechanism. So that's what we're seeing here. Green represents a bias improvement, purple represents a bias degradation. So we're looking at resolution. EPA region 8 includes California, and 1 and 2 include New England, New York, New Jersey. So that's why we're seeing improvements there. And then in the summertime with additional chemical complexity, we see bias improvements as well. For PM2.5, we have less agreement with observations, and a large part of that's due to nitrite aerosols not being directly included in the simulation. But we can still see shifts in the model bias. And here, the higher resolution model tends to predict PM2.5, higher PM2.5 in population areas and lower concentration in rural areas. And then we see a large shift in summertime using the Mozart TS2 mechanism. And that's based on different high NOx SOA pathways that have been included in this model. And so when we translate this to population weighted metrics, we're calculating, this is for ozone, where the metric of interest is the maximum daily average 8-hour ozone concentration, or MDA8. I've basically separated each one of the regions to see how the concentration shifts for either, this is for each different chemical mechanism or resolution improvement. So this is for the 1 degree, and this is for the basically 1 degree minus regional refined. This is for TS2 minus TS1, shown in top and bottom. And for higher resolution tends to estimate lower exposure, and I'll get into that in just a sec. And it basically goes from a 25 to 35%, 35% reduction to a 25% increase, where chemical complexity has a near zero shift, but a smaller range. So for ozone, chemical complexity does not seem to be as important in population-weighted metrics. If we look at PM2.5, again, we can see that both chemical complexity have, that we have a reduction in PM2.5 exposure. If we look at, sorry, an increase in PM2.5 exposure if we look at the higher resolution model, and then we also have an increase if we do use reduced chemical complexity. That's what's being shown here. So horizontal resolution estimates up to a 60% increase in population-weighted PM2.5 exposure, and chemical complexity results in a 10 to 30% reduction. So if we increase the chemical complexity, we estimate reduced ozone concentrations, population-weighted ozone concentrations. So I did want to discuss real quickly some of the items that we found. This gets into one thing that I sent a message to Tim about, but here we see a persistent overestimate of ozone if we're comparing it to surface monitors. So this is an aggregate of all EPA surface observations, and then this is daily MDA8, again aggregated for the model results, and we can see that we're overestimating this. But we do see that using Musica, which is the blue line, we are getting some specific events that we don't get in the 1 degree model. So here you can see this blue peak here that matches the observations. And we see a smaller peak here in California, Nevada, Arizona. This is due to NOx titration near source regions. So in population centers, we're getting NOx titration of ozone, which better matches the observations. And then the second thing that we did to try and improve this bias, which is shown in the results prior, is we attempted to do a surface concentration for our comparison to observations. So this is following Zhang et al. And the same method that's used in GeoSchem, where you have your surface roughness parameter, your deposition velocity, and first level ozone concentrations. These are output from the CLM, and then we use this to correct for our surface ozone. And the results of that are shown here, and we're still analyzing this a little bit further using some different parameterizations. But as you can see, we're much closer to matching the observations using this surface correction. And I think for the sake of time, I'll skip over this. But I just wanted to touch on the conclusions and some of the next steps. As I hope I've shown here, Musica does allow for the modeling of pollutants at exposure relevant scales within the fully coupled CESM. And improvements in resolution and chemistry improve the model bias with respect to surface observations, which is a good thing, and that's what we were hoping for. And these changes have significant impacts on model exposure to health relevant pollutants, which therefore impacts the burden of disease. So we're finalizing the analysis of this in preparation for a couple publications, that one that I'm writing and one that Becky Schwantes, who's now at NOAA, is writing. But if you're interested in this work, and particularly in Musica, I would recommend going to the Musica wiki. It has a great deal of information that a lot of us in ACOM and throughout NCAR put together, particularly on dealing with unstructured grids. And then I wanted to kind of end with just kind of what I see as coming up next, or what I've learned from this process. One thing I think that we should put into the model diagnostics that I've done as offline calculations now is things such as population and population-related exposures, along with MDA ozone. It actually takes up quite a bit of memory to write out the 1 hour concentrations, where if that's something we could calculate online, I think that would really save some of the efforts that we have. Particulate nitrate is an issue for the current health analysis, but the validation and implementation of Mosaic that Dusong has been working on will help with that, but at an added computational cost. Additionally, if we want an accurate representation of surface level concentrations, we really need to have additional vertical resolution. Right now, our first level is way too high to estimate surface concentrations, and that leads to some differences when we're discussing exposures. So I think that's something that we should kind of focus on primarily. And then one of the things that Haipeng talked about that I'm very excited for would be HEMCO would actually make this last bullet point a little bit easier, which is if we're interested in exposure, some online calculations of a kind of weekly or diurnal trends in emissions would really help. And then also injection height in lieu of 3D emissions fields. So for things like biomass burning emissions or stacks from power plants, there could potentially be a computational advantage to doing that online instead of reading and writing out to 3D fields. And I think with that, I will take any questions.
Thank you, Forrest. Thanks for bringing up these suggestions for diagnostics and other things. Joan Alexander asks, your point about differences with resolution is made and is very clear. However, could you say a bit more about how errors in meteorology could influence uncertainties in your impact calculations?
Yes. So I don't have a lot on that in here, but we did run with a number of different nudging schemes and nudging times using the new nudging parameterization that's in CSM 2.2. And that was, a lot of that was dealing with comparisons to flight tracks, so airborne observations, but we also did do a surface comparison. And we've kind of come to the conclusion that the current 50-hour nudging scheme is adequate for some of the health impact calculations. But if you're interested in specific flight campaigns, you may need to have a more aggressive nudging scheme. But since we're looking at the health impacts, we're really not focused on acute concentrations. We're more focused on chronic exposure. So the 50 hours seems to be appropriate for that.
Good. A couple more questions in the chat, and I'll let you answer those in the chat. And we'll move on to the next talk, which is by Wenfu Tang, who's an ASP postdoc at NCAR. And she'll present Musica version 0 simulations of fire impacts on air quality during FireX.
Can you hear me? And
I can hear you.
Okay, cool.
Yep, that looks good.
Cool. Okay. Hello, everyone. I'm Wenfu Tang. I'm an ASP postdoc at NCAR. Today, I'll be presenting my ongoing work on Musica simulations of fire impacts on air quality during the 2019 FireX field campaign. So before I start, I'd like to acknowledge all my co-authors, especially Luisa Emmons, Rebecca Bajos, and also Christine Whitmire. And now let's get started. So here's some background information. Forrest has already given a very nice introduction to the Musica version 0, so I'll just skip this. And so FireX campaign. So FireX was conducted in summer 2019, and it provides comprehensive observations to study the impact of wildfires and also agricultural fires in the United States on the air quality and climate. And this is a nice figure, a nice picture of the NASA DC-8 aircraft, which was deployed during the FireX campaign. And so this study is designed to answer these three questions. So the first question is, how is regional air quality impacted by fires in the continental United States? Second, how well does Musica capture such impacts? And the third question is, how could we improve Musica simulations of these fire impacts? So to address these three questions, we conducted these 7 simulations as listed in this table. So the first simulation is a CAM-chem simulation with a spectral element dynamic core. The resolution is 1 degree by 1 degree, as you can see by this figure. And the second simulation is uses the CAM-chem IC with regional refinement. So within this refined region, the resolution is 14 kilometer. So by comparing these two simulations, we can learn about the impact of the resolution on the model simulations of fire impacts. And the second and the third simulations are the same simulations, except they use different fire emission inventories. So QFED and FIN 2.2. So by comparing these two, we could learn about the sensitivity of the model results to the usage of the fire emission inventories. And all right, so fire emission inventories are usually daily. That means the fire emissions are assumed to be constant throughout the day. However, in reality, fires and also fire emissions have a strong diurnal cycle. And because daytime and nighttime meteorology and chemistry can be very different, therefore adding a diurnal cycle to fire emissions in the model could potentially improve the model simulations of the transport of fire-emitted trace gases and aerosols, and also improve the model simulations of fire-related chemistry. So therefore, we conducted these 3 highlighted simulations to see if applying diurnal cycles to fire emissions could improve the model results. So we tested 2 approaches. We tested 2 approaches to apply the diurnal cycle. The first one is very straightforward. So in this Lee et al. 2019 paper, they came up with this characteristic diurnal cycle for all fires within the CONUS region. So what we did was applying this diurnal cycle to all the fires in the FIN 2.2 emission inventory. So that's this case. And this curve is supposed to be only for the CONUS fire. However, we still have another sensitivity simulation applying this curve to all the fires around the globe, just to get an idea how would this impact the long-range transport of fires to the CONUS region. And the second method is more computationally expensive and complicated than the first one. So we extract the real diurnal cycle of fire radiative power from the GOES-16 geostationary satellite and applied that to the FIN 2.2 emissions. And in this case, every single fire would have its own diurnal cycle. And lastly, we also have a simulation with the fires within the CONUS turned off. By comparing the fire on and fire off simulations, we can answer this question: what are the regional impacts of North American fires? And let's first of all, let's compare the carbon monoxide simulated by Musica with the DC8 measurements during the FireXAQ campaign. So for each scatter plot, the x-axis is the observed CO and the y-axis is the modeled CO. The first row shows the comparisons with all the observations from the DC8. And the second row only shows the comparisons with the observations that were classified as fire plume observations. So if you look at the first 2 cases, you can see by increasing the model resolution from 1 degree to 14 kilometers, there is a significant improvement in terms of the agreement with the DC8 observations. And if you look at the second and the third columns, you can see that the simulations with the FIN 2.2 inventory have very slightly higher correlation and lower mean bias. That's a good thing. And if you compare these 3 simulations, the last 3 simulations with fire diurnal cycle applied with the this third simulation without the diurnal cycle, you can see that the applying diurnal cycle of fire emissions can improve the model agreement with the observations as supported by increased correlation and decreased mean bias. And if you look at the bottom row, these points here as an example in this green circle. So these points are likely to be the fire plumes missed by the model. And here, this slide shows the observed and modeled CO in the time order. So the x-axis is the observation ID ordered in time. So the first figure is the observations, and the rest 3 figures are 3 selected musical simulations. And the black dots are the background observations, while the red dots are the plume observations. So as you can see, most for these wildfires at the first part of the field campaign, their plumes are reasonably captured by musical simulations, especially after applying the diurnal cycle. And one exception is a shady fire, which was missed completely by the model. And this is likely due to the fact that this is likely because that this fire event was missed in the emission inventory. And in addition to the DC8 airborne observations, we also compare the musical simulations with the EPA ground sites observations of PM2.5 and ozone during the 5XAQ period. So this map on the upper left shows the average value of the observed PM2.5 during the 5XAQ campaign. And the figure on the right shows the probability density distribution of the model bias comparing to the EPA sites only within this red box. And the two figures at the bottom are for ozone. So as we can see by this plot, increasing the model resolution improve the model agreement with the EPA ground sites, as shown by this blue line. And if we compare the simulations with and without the diurnal cycle applied to fire emissions, we can see that applying the diurnal cycle clearly improves the musical agreement with EPA observations of PM2.5, regardless of whichever the diurnal cycle approach was applied. Interestingly, and the change in the ozone bias does not seem to be changing. Okay, and now let's look at what are the regional impacts of North American fires by comparing the fire on and fire off simulations. So this slide shows the monthly averaged ozone and PM2.5 from the CONUS fire on and CONUS fire off simulations, and their differences are also shown on this slide. So as we can see, North American fires significantly impact the air quality over the Pacific Northwest and the Southeast regions. And this slide shows an example of regional fire impact on air quality. So I picked this Colville East First Street site because this site is very close to the Williams Flats fire. Williams Flats fire was one of the largest fires measured during the 5XAQ field campaign in 2019. So as you can see in this time series plot, the black line is the EPA observations, the red line is the musical fire on observations, and the blue line is the musical fire off observations. And as you can see, the air quality during this time period was significantly impacted by the Williams flat fire. All right, and this is an ongoing project. So here are the preliminary conclusions and plans for the next step. With that, I'll stop here and take questions. Thank you for listening.
Thank you, Wenfu. Very nice. Do you want to say something about Ben's question, which is, have you checked the vertical structure of the errors? Because is the model missing the altitude of the plumes?
Oh, yes. So when I interpolate the model, the model results vertically to match the plumes, I actually checked the 3 layers, the layer where the plume height actually located, and the layer above and below, just to see which, if the plume is in the wrong
One
layer.
of the other layers. Yeah, it's a tricky problem. Thank you. I think in the interest of time, we'll move along and people can ask more questions in the chat. So our next speaker is Behrooz Rusitalab. Sorry, I realize I haven't practiced that. Tell us about online global regional air quality modeling using Musica over India. And I just wanted to say Behrooz is a grad student at the University of Iowa and is the ACOM Ralph Cicerone Fellowship this year. So you can start sharing your screen.
Sure. Hello, everyone, and thank you for giving me this opportunity. Do you see my?
Yep, looks good.
Okay.
Perfect.
So yeah, my name is Behrooz Rusitalab, and I'm a PhD student in University of Iowa. So since Forrest and Wenfu talked about Musica, I just only mentioned that I think in air quality modeling aspect, a multi-scale model is very useful because of you can have boundary conditions and basically an air system chemical transport model all in one framework, and it's a very exciting model. And Musica is, of course, the one that we are using here. And I will not talk about the Musica itself, but in our work, we are focusing on India, and I think Musica is useful for India specifically because India is getting affected by mostly long-range transported pollution, specifically from Middle East deserts and like dust emissions from north of India. And on the other hand, studies have shown like the global ozone burden of different regions and like India. And I think Musica is helping us to have a better presentation of that. So in this presentation, I only show some of our preliminary results for Northern India. And in these results, I compared the impact of the resolution on some of our simulation results. So when I say any 30, I mean that we are running the Musica model with 1 degree uniform grid over the whole world. And by any 30 times 8, we mean like 1/8 resolution over northern India and 1 degree over the rest of the India. And here I am I'm showing the average surface PM2.5 concentration in one sample month here in June 2010 for these two simulations. And so basically what we see is if we just if we look at the world except for the India region that we are using different resolutions, we see some differences like for in Africa or Australia that we still are studying that to see what's the difference. Is the difference because of the dynamics or because of the something is happening with the grid? So, but for now, I'm focusing only over this region that is having different resolutions. And if I focus on that region, here I'm showing the PM2.5 concentrations in the high resolution run and here in the low resolution run, basically. And after regrading them to similar resolution, we can get the difference between these two models. So there are some interesting results here that we see. For example, over north of India, we see higher PM2.5 concentrations that are basically because of the dust emissions here. And but this is interesting that over the ocean, when we have a higher resolution, we see lower concentration, and this is something interesting, and I still don't know the reason. But one of the results of using a high resolution model is that we see some local new emission sources, and mostly, I mean, the dust emission. So this is over the west of India, and we see that when we have a high resolution run, we probably have higher wind speed, and because of that, we are getting more dust emissions compared to a low resolution run that we don't see any dust emission here. But now I want to look at Delhi, so and see the difference between these two scenarios for in more detail. So if we focus on Delhi in a 1 by 1 degree region, in a lower resolution run, we only get one value, but in a high resolution one, which is in 8 times higher and about 14 kilometer resolution, we get about 61 grid cells within this region that is centered over Delhi. And here I'm showing the concentration and distribution of the concentrations over Delhi. So the black line shows the low resolution value. And as I said, it's only one grid cell, so it's one line only. And the red line, the red distribution shows the density of those 61 grid cells. And the line shows the mean of these 61 values. And I'm showing that for different vertical levels. So what we are seeing here is that we see that the average of the high resolution runs is not similar to the coarse resolution run. So it shows that when we go to a higher resolution model, we will see different concentrations. And when we look at the distribution, we see that the coarse resolution value is kind of coming from the tail of the distribution of the high resolution run. So it shows the difference between high resolution and low resolution runs. And when and here I'm showing these mean values for the first 10 or 15 vertical levels. And we see that for PM2.5 concentrations, when we go to higher levels, the difference is getting decreased until some point in fifth or sixth point at 900 hectopascal, and then again gets increased, the difference between these two. So this is something that is happening over India because of the resolutions, and we are seeing, and then we look at the different species over this region. So I'm basically showing kind of the same thing, but for PM2.5 composition at the surface layer. And what we see here is that we are seeing very different composition and distribution of composition for the natural sources like sea salt and dust. And this is interesting that we basically see lower sea salt over Delhi in a high resolution run, which is kind of consistent with what we are seeing here, that in a high resolution run, we have lower PM2.5 concentration over ocean. And when we look at the Delhi, we see lower sea salt over Delhi in this simulation. So I'm also looking at ozone concentration for the similar analysis. And we kind of see that the trend is similar in these two simulations, but in the higher resolution, we have much lower ozone concentration at the surface, up to like 20 ppb lower. And one possible explanation for that is can be that we are looking at June, which is a transition between pre-monsoon and monsoon season. And it's the reason may be that we have more precipitation over these the hills of northern India, and as a result, we have lower ozone because of wet deposition. But then when we look at the distribution of similar analysis, we see similar performance that in a high resolution run, we have lower ozone concentration. And one reason can be because of the wet deposition, and one reason can be because of more titration that I will show in the next slide. But we see that we are systematically have lower ozone concentration in all the vertical levels when we compare these two simulations together. And the difference, for example, at surface is about 5 ppb between these two scenarios. And again, June is not basically a high ozone month in India. And maybe if we look at May or April, we will see higher differences on that. And these results can, and these ozone concentrations can change, can affect the global ozone burden results. And here I'm also showing the some of the precursors of ozone, and we see that basically the main difference is for CO and NO2 and hydroxide, and this is something that we should study more, that why, and see that the difference between the NO2 concentration and the variation is because of the meteorology or just because of the chemistry. But we see that isoprene and formaldehyde, basically isoprene as a natural precursor, doesn't change. And so as a summary, we see that high resolution can lead to more emission sources, and it can have different effects on different vertical levels. But for our next steps, we are going to focus on year 2017 and basically November, because we had a very extreme pollution event over northern India in November 2017, and we would like to compare our results with Musica with WACCM results. And thank you for your time, and I'm happy to answer your questions. Thank you.
Thank you, Bruce. It's very exciting to see Musica branching out into a new region of refinement. There are a few questions in the chat and they look a little lengthy, so I'll let you answer them in the chat, or we can come back to them in the discussion section. And we'll move on to our next talk by Jun Zhang, who's a graduate student at the University of Illinois and an ASP graduate visitor in ACOM this year, though virtually. And she's going to talk about representing Asia summer monsoon using Musica.
Can everyone see my screen?
Yes, that looks good.
Okay.
Perfect.
Hi, I'm Jun. I'm a PhD student at the University of Illinois at Urbana-Champaign. I'm working with Professor Donald Ubos. And currently, I'm also an ASP graduate visitor at ACOM virtually, working with Douglas Connaughton. Today, I will be talking about representing Asian summer monsoon using regional refinement with Musica. This is ongoing work that I have been working on for the last 2 months during my virtual visit at NCAR. First, I would like to thank all the great support and help on this work from Simone, then Sean and Laura. Okay. A little bit background of Asian summer monsoon and the motivation of studying it using Musica. Asian summer monsoon is the largest meteorological pattern in the Northern Hemisphere summer season. It is an efficient pathway to transport boundary layer air to the UDLS through deep convection. This figure here shows the MLS carbon monoxide at UDLS during the Asian summer monsoon season. A typical trade mode is associated with Asian summer monsoon. The large anticyclone over the Tibetan Plateau is connected to the deep convection in the lower troposphere. The air mass lofted by the convection from the boundary layer and subsequently transported to the West Pacific UDLS through subseasonal scale eastward shedding events. Properly represent of these processes in the models helps to characterize Asian summer monsoon chemistry climate interactions. The biggest motivation of using Musica is to provide chemical forecast to support ECLIP mission objectives with a focus on the West Pacific region. ECLIP is the Asian Summer Monsoon Chemical and Climate Impact Project at NCAR. It is designed to provide in situ measurements necessary for addressing the science questions of Asian summer monsoon chemistry climate impact. It will investigate the transport pathways of the Asian summer monsoon uplifted air from inside of the anticyclone to the global UDLS. It will also explore the ozone chemistry and budget, including ozone depletion substances and ozone precursors. It will also investigate chemistry-climate interactions from short-lived climate pollutants and the information on aerosols for determining the radiative impact. For now, from previous talks and Luisa's talk, we know that Musica is a new model framework of CAM-chem, which enable chemistry and aerosols to be simulated at a finer resolution. In order to run Musica, we first need to create a grid for our region of interest. This figure here shows the grid we have created for our Asian summer monsoon study. The base map is in it's a cube sphere grid, a spectral element dicore. The base map is in 1 degree with our interested region in a quarter degree around 30 kilometers, and the transition zone is around 50 kilometers. This grid covers the Asian summer monsoon deep convection, anticyclone, and over the Tibetan Plateau, and eastward eddy shedding over the West Pacific region. The regional refinement allows for better representation of regional processes and chemistry of surface emissions. And the grid also covers both natural and anthropogenic emission sources from South and East Asia. Once we have the grid ready, we will need to process the input. This include to run the model. This including initial conditions from for both atmosphere and land, and also meteorological and emission data. We obtain the atmosphere initial condition by spinning up CAM-chem using SE-NE30. Then we run the model without chemistry to spin up the net initial conditions. All the input are needed to be regraded to our regional refinement grid before we run the model. The steps and scripts and tools that used to process the input can be found on this Musica wiki website and the GitHub page. The emission scripts are currently being updated, and the logging on the model levels are also being performed. In order to test our model results, we run Musica for 2 months to reproduce the dry run period in July to August 2020 for Eclipse campaign and compare Musica results with other model results. The model cost is around 150K per year. So we will compare Musica's results with the other 2 models in the 2020 dry run for chemical forecast. One is a WACCM 6 driving with GEOS 5 winds in 1 degree and 88 level. Another one is NASA GEOS model in a quarter degree 72 level. These models differ in their setup resolutions and configurations, and as well as their chemistry and aerosol schemes. We will focus on the large eastward shedding events on August 2017 in 2020. The figures here show the carbon monoxide at 150 hectopascal from Musica, WACCM, GEOS, as well as MLS satellite. And the carbon monoxide is lofted by the convection from the Asian boundary layer and subsequently transported to the West Pacific UDLS. Compared to MLS, Musica, WACCM, and GEOS, all 3 models have captured the large eastward shedding events, but at a different magnitude. Musica and GEOS shows stronger signal than WACCM. This could be due to the difference in their horizontal resolution. Both Musica and GEOS has a horizontal resolution in a quarter degree and WACCM compared to WACCM in 1 degree. Now we are looking at the ozone in the shedding events on the same day. The left and right column shows the results from Musica and WACCM. The top panel and lower panel are for 100 hectopascal, 100 and 150 hectopascal respectively. So compared to WACCM, Musica show a much lower ozone level from tropospheric air in the anticyclone confinement, as well as the center of the shedding shedding event at both the 100 and 150 hectopascal. This indicating much stronger lofting from Asian summer monsoon and associated with stronger shedding events in Musica compared to WACCM. High level of ozone indicating air mass of stratospheric origins can be found at the south of the eddy shedding. At 150 hectopascal, where the air is more isolated from stratospheric air, while at 100 hectopascal, there is a clear signature of a stratospheric mixed ozone in shedding events. In addition to air originating from land, air of marine origins can also be transported to UTLS region. The figures here show the Brom form of oceanic sources during the shedding events. Compared to WACCM, Musica shows a stronger enhancement in Brom form level, indicating a stronger influence of marine air in the shedding events. Brom form as a very short-lived ozone depletion substance, the enhanced level is likely leading to an impact on the stratospheric ozone layer, which would be interesting to find out during the eclipse campaign. Musica also shows a higher level of water vapor lofted by the Asian summer monsoon. The moist air brought up from troposphere.
We're not seeing your slides change. We're still on ozone.
Oh, can you see the slide change?
No, it's still on the ozone in the shedding event. Can you just jump out of the presentation and start over? And
okay, now can you see it?
No.
Okay, I will, sorry about that. I will pause sharing and share again.
Unless it's only me.
Oh, really?
No, it's not just you.
Okay.
Sorry about that.
Not sure what.
Can you see my screen now?
It started screen sharing.
Huh.
It's all dark right now, unfortunately.
Yeah, it's not, we can't see it.
Okay. So weird. Still can't see?
No.
Why did you go out of presenter mode? On your desktop, just exit presenter mode or
yeah,
she did that.
I stopped sharing and share again, and it seems not working.
Why don't you just read us your conclusions, because we're running out of time.
Okay, sure. So the summary is that we have successfully running a Musica with Asia grid for the first time, and regional refined CAM-chem represents the Asian summer monsoon really reasonably well and agrees well with GEOS 5 and satellite observations. Musica is a very important tool to study Asian summer monsoon and its chemistry-climate interaction, and to support the chemical forecast for eclipse campaign in the future. And this work is still at the very initial stage. We still have a lot we wanted to explore, but it's definitely great to say that Musica is working for this new grade. And next, and in the very near future, we will update the emissions. The new emissions include new VOC emissions over China, and we will produce new spin-up simulations with CO tags, and we will incorporate more complete halogen chemistry such as iodide chemistry, and we are also planning to compare the CAM-chem regional refinement without refinement, the normal version of CAM-chem, just to see how much difference the regional refinement make. And we might also test other grade that have a second layer over the West Pacific region that can better capture the chemical signature associated with typhoon during the monsoon season. And eventually we will prepare the model for the eclipse campaign study. Last but not least, I want to acknowledge the great opportunity provided by the advanced study program to work on this project and also to collaborate with those amazing scientists at NCAR. Okay, thank you.
Thank you, June. We saw this last slide there.
Sorry, I had a very cute animal there.
It's yes, we're sorry you can't be there in person with us. Great, we'll let you answer some questions in the chat, but I think this is very exciting progress as well to see Musica for another Asia grid. And so finally, sorry, I did not keep people well on time. Our last talk is by Douglas Hamilton from Cornell University. Are you still here? Oh, there you are. Yes. To talk about coupling the mechanism of intermediate complexity for iron into CESM CAM-6. Great. That looks perfect.
Lovely. Good stuff. So thank you very much for the opportunity to come and talk today, maybe about something slightly different for some folk on the call, about the iron cycle. So first of all, I'd just like to say thank you to all of my collaborators and co-authors in all of the support that they've provided so far in developing this model. So much what I'm going to talk about is the mechanism of intermediate complexity for modeling iron, MIMI. The technical description paper for this is out in GMD in 2019. So if you're interested in some of the finer details or want to see how it could potentially work for you in CAM, then please do go and have a look at that paper, and feel free to reach out to me as well afterwards. I'm happy to support anyone who's interested in this particular part of the Earth system. So why should we study iron aerosol? We already had some great talks today about human health, but while the presence of metals in PM can't explain all of the toxicity in PM, it is also mechanistically plausible that the relationship between sulfate and iron is enabling the formation of toxic free radicals. For aerosol radiative forcing, it's important as iron is a very strong absorber of radiation. So this impacts our understanding of the direct radiative forcing, and also changes in atmospheric burden over time due to anthropogenic activity. But the real effort here and the motivation behind developing MIMI was the question of the ocean biogeochemistry. So marine net primary productivity converts CO2 into organic molecules via both photosynthesis and chemosynthesis. This produces oxygen as a byproduct, which is then supporting terrestrial life. But at the same time, those organic molecules which are being produced in the ocean can sequester CO2 down into the depths as those molecules fall, so therefore effectively locking it away. Marine microorganisms account for around about half of the Earth's net primary productivity, and in around about 30% of the oceans, iron deficiency relative to the cellular demands is restricting the biomass accumulation. So it's really quite important for us to get a handle on where this iron is being produced and where it is being deposited. There's a brief overview of the development of MIMI. So it started being developed in CAM4 by Rachel Scanza during her PhD. The development went stepwise. First of all, we implemented dust minerals. So there's 8 minerals being transported around in the model
5 of which have an iron component. And we added in extra iron sources and the chemistry. And finally, this was then developed and ported over to the MAM modules. So in total, at the moment in MIMI, we are carrying 3 different sources of iron. We have iron from dust, iron from fires, and iron from anthropogenic sources. Anthropogenic sources here is relating to industrial and transport pollution, but also there's an important source in things like metal smelting as well. The iron, when it's being evected around the model, is carried in 2 different traces. We carry the insoluble form and the soluble form. And that's important because it's actually the soluble part which is thought to be the bioaccessible iron to the phytoplankton. So that's the part that we're really interested in understanding how much of that we are depositing into the oceans. During transport, the insoluble iron can be converted to soluble iron though, by undergoing a range of acidic and organic processing. And we have some of those in the model. And then it's being deposited to the ocean, which is what we're interested in quantifying. Overall, the cost of running all of this, all the extra traces and the extra chemistry in CAM6 is around about 10% more on the base model. So it's not too expensive in comparison to what is actually going in there. So how much iron do we have? How much iron is being emitted into the atmosphere? So here we've got some time series plots from 1980 to 2015. We're looking at the emissions across all 3 different versions of CAM and their means, so CAM 4 to 6, and it's got matched nudge meteorology there. What's important to kind of look at here is the difference between the dust emission sources in the yellow and the 2 pyrogenic emission sources down here, which is the fires in the red and the anthropogenic sources in the blue. You can see for the total amount of iron that the dust is really dominating the signal here. This is a log scale, so it's a couple of orders of magnitude higher. But when we're getting to this bioavailable, the soluble iron emissions, that difference is attenuated quite strongly. So it's important that we're considering these different sources of iron in the model, not just the dust iron, which has kind of been more the traditional source that people have been thinking about. And these differences are caused by difference in the composition and the mineralogy of those different sources, with pyrogenic sources being much more soluble at emission, so a higher solubility, which is the fraction of soluble to total, than the dust sources. So it's been observed that during transport with distance, as the aerosol pH can lower, we end up with a higher solubility. So that's this transformation of the total into the soluble. So we parameterized that in the model. And that required us to introduce a parameterization for pH. So this is very basic. What we've done is we compare the main acidic species sulfate to the main base species calcium. And if one's higher than the other, then we prescribe a pH in the aerosol. And when we compare this, though, to more advanced representations like isoropria, we actually find out that a lot of that spatial pattern is being captured. But I would welcome any discussion on how to efficiently, with low cost, perhaps improve how we are representing that aerosol pH. So if you have any ideas, please do let me know. So how's the model doing? So here we're looking at a 5-year mean of the model simulation of the total iron compared to the observations that we have available. The observations are aggregated onto a 3x3 grid. You can see that the model's doing well. It's capturing most of the spatial distribution in the total iron. If we look over at the scatter plot of what that looks like, we can see actually that close to sources up here in from Northern Africa, the model might be overrepresenting dust sources, whereas far away over the Southern Ocean, we might be underrepresenting these dust sources, the scale by the pyrogenic iron. And that's consistent actually across other iron models as well. So this is something for us to be working on. When we look at the iron solubility, so that's that fraction of the soluble iron to the total iron, we can see that there's a lot more diversity actually in the observations. You can have very high fractional solubilities close to observations of very low fractional solubilities. So this proves to be a challenge for the model in being able to capture that. One of the things that's maybe not helping is that we don't have very many observations. It's very expensive to send the ships out into these remote regions, and we have perhaps 1 or 2 to 3 observations. These observations are only taken over a 24 to 48 hour period as well. So it's very, very sparse. And also at the model level, the variability in what we're seeing in the iron is really dominated at the daily level. So it's highly temporally variable. And that's due to the episodicity in the major iron sources, both dust and fires. So those two are part of the problem that we're trying to work on to better constrain the solubility in the model. So where do we care about the iron being transported to? So here we're looking at ocean concentrations of nitrogen on the left and phosphorus on the right, which are 2 macronutrients required for productivity. And the red dots are where we've had campaigns go out, and iron addition in these regions has been shown to increase the productivity. So these are classed as high nutrient, low chlorophyll regions, and it's basically in the North Pacific, the Southern Ocean, and the Equatorial Pacific. That's where we're really interested in how much iron is entering those ecosystems there. So then we wondered, is human activity perturbing the amount of iron which is reaching different basins, in particular these high nutrient, low chlorophyll ones? So we had a look at 3 different time series, 3 different timestamps, the pre-industrial, the present day, and the future under RCP 4.5. And in the pre-industrial, we also ran some extra sensitivity simulations with higher fires. And what we can see quite clearly is that, yes, there's been a strong anthropogenic perturbation here to the amount of iron that's being deposited. There's a lot more iron being deposited in the Northern Hemisphere and less to the Southern Hemisphere. And when we look out to the future, that actually reverses, where we have higher fires producing more iron in the Southern Hemisphere, which is then increasing the deposition there. And then air pollution controls are reducing it slightly in the Northern Hemisphere. And what does that mean then for the biogeochemistry? So we took our soluble iron deposition fluxes in A here across our time series, and we've run it in the Beck model, which is in POP as well. And what we can see is that for net primary productivity, it's actually pretty insensitive really to these changes over time. But the community structure itself, so what is actually growing on addition to iron, is highly sensitive to, or much more sensitive to, the changes in fluxes. And diatoms are much larger than other phytoplankton, a lot heavier. So that means that the carbon export is actually more efficient, because if you have more of the larger guys growing, then they're going to be able to export more carbon out of the system. So although the primary productivity itself is quite low in changes, we can actually get large shifts in the export production because of that community shift. And finally, when we look across our 3 different sources in terms of what the carbon export efficiency is per gram of iron being deposited to different oceans, we actually find that it's actually fires which is potentially stimulating the most amount of export. So again, this is why it's important for us to be thinking about different sources of iron and not just dust. So I'll end on that slide there and just say, anybody who's interested in iron modeling for any particular reason, please do reach out. I'll be more than happy to help talk through how to get this set up in any studies that you have. And thank you very much.
Thank you. That was very interesting. It's nice to hear a different connection to other model components and ocean biogeochemistry than we've been hearing. Mary has a quick question. Can the iron aerosol prediction be used for iron catalyzed cloud chemistry reactions that form sulfate?
Yes, it could, in theory, absolutely. There's no reason why we carry the iron in both the cloud-borne phase and in the interstitial phase. So if you put the reactions in to increase that, then you could end up with more sulfate. Yes.
Oh, great. for the aerosol pH, you may want to consider using the mosaic scheme that we've been implementing, the gas aerosol exchange. Our primary motivation was to get nitrate aerosol, but it will have the pH of the aerosols. It's quite a bit more expensive. So, and you need to run it with chemistry. It can't just run with CAM by itself, but that's something to look into maybe.
Thanks. Yeah, I mean, we were trying to avoid overly complicating and the runtimes, which is why we've gone for a simpler parameterization. But yeah, maybe there's something in Mosaic that we can look at to help.
Yeah.
Thanks.
Oh, great. Thank you very much. And now, if people have the stamina, hopefully you've people have been wandering off for breaks and coffee and as needed. Maybe we can spend a few minutes of on discussion. We can also have questions for the previous talks, but let me just put up a few top points that we wanted to give you all an opportunity to discuss or provide comments on. We've talked about a number of developments that are in progress, but maybe there are other things people are working on that they haven't had a chance to talk about. They weren't ready to give a presentation on. We'd like to hear about them. What are your development priorities? We're also going to have a wrap-up discussion in an hour and a half. So if you can come back for that, that will be another opportunity to bring up what you think should be in the next versions of the model and put in. Often we ask if some people would like particular comp sets. You want some out-of-the-box configurations. We'd like to hear about those. Forrest brought up some diagnostics. I noticed Tim also talked about OH reactivity that could maybe be implemented in the model as a diagnostic. And we could talk about what if people are involved in various multi-model activities. So, does anyone have any questions, comments, wishes? Just unmute yourself. And everyone who presented, please remember to send your presentations to Elizabeth as in the chat.
This is Forrest, just kind of following up on one of my discussion points from my talk. And I think that this is of interest, not just to me, but also to people looking at some of higher altitude stuff. We had some internal discussion about changing vertical resolution, basically adding it in the boundary layer and at the tropopause. Do you know any status update of that, or if there's a timeline or plan for testing that?
I think there was some stuff going on in the, I don't know if you had a chance to listen to the CAM sessions or the earlier sessions, but Brian Medeiros and others working on a high vertical boundary layer scheme that will be added and tested. And at the moment, I think there are some initial test runs, but it hasn't been included. Chemistry hasn't been included yet. So once that is included, we can start looking in that. And it's work in progress. It's part of the work with the workhorse model and stuff like that. So yeah, okay. It's gonna come.
Okay, thanks, Simone.
I think there was quite a bit of discussion in the chat regarding the CAM's chemistry as well as the HEMCO scheme. So if there are not any other thoughts, we could also pick that up in person, Luisa. I just wonder because that was quite a long back and forth.
Yeah, yes, I was going to say that too. If anyone has further questions about any of the talks, like to elaborate on the chat answers or questions.
I think I have a question on the CAM's scheme. I mean, there was a bit of questions on how much it is coupled to a different model, and maybe that could be summarized again to really the whole atmosphere model, and since this is mostly chemistry.
I missed the first part of your question. What the key question there?
Oh, I just had a question on, a lot of people asked how this is coupled to a 3D model, and maybe Oriol could.
Oh, camp. I missed camp.
Oh, camp. Yeah, no, I said camps. Sorry, I meant camp. Sorry for that.
Is Oriol still here? It's late there.
Oriol doesn't seem to be on the line. But,
so Matt is here.
Oriol had to go, so he asked me to listen for any questions. I'm sorry, I missed the full question though. Is it about connecting CAMP to 3D models?
Yes.
Right now, Oriol's working on connecting it to the Monarch 3D model that they have developed at BSc. It's ongoing work. But they're working right now on getting the carbon bond 5 mechanism that he showed results for in a box model working in the 3D model.
There's also an effort yet to integrate this model with CAM and evaluate the ability of CAM to handle this sort of flexibility. We're supposed to do that evaluation over the next 6 to 8 months.
So how does that interface with musicals that we heard about in the CAM? Is it through this musicals activity or?
Well, so the question there is whether the musicals activity wants to actually define an API that would be used for chemistry. At this point, I have yet to have seen the scientific justification, but the question from a programming standpoint for musicals that drove it was the need to, or the wish to be able to transport aerosol models between different host models. And the way you get transportability is you define an interface. So what we've supported is the idea that maybe the community could get together and define an interface, an API for aerosols and chemistry. But we'll see where that effort goes. Where that effort goes. The API that's in CAMP could be used as a potential first guess at that, but I think we would probably find that we would want to expand significantly those capabilities to support other capabilities.
Maybe just a remark on that. Yeah. So they're part of the musical as well. So I think since they're the only one that they have this API, they have thought about it. I think we should, take advantage of that and have some discussions. They can explain what they have done and what are the weaknesses and strengths of their approach and how we can generalize it to other models. Yeah, that's definitely in the working. So, and the musical is supposed to build this general interface or aerosol programming interface. I don't know if you're going to get to the programming interface, but the interface that will allow us to use libraries of aerosol modules and interface with different host models. Does it answer the question?
The thing that would make the aerosols and chemistry transportable would have an API, which is an application programming interface. That idea is not specific to aerosols. One of the major differences is it's not just a set of subroutines and basic data types. So you actually abstract that away a little bit and provide an API. Just like in when you write a netcdf file, you have to say what you're doing with a netcdf file before you put the data in it. that's what an API does for you. So there's a reason people use netcdf files rather than flat data ASCII files. And in the same way that provides transportability for data by documenting the data, an API for aerosols and chemistry would document the inputs and the outputs in a way that makes it transportable. I don't know if that helps.
I have a question actually, Andrew, maybe just on that aspect. So in CAMP, the chemistry, the gas phase chemistry and aerosols are in the same solved together. So then the API is above that, right? Whereas in musical, we are basically just talking about separating the aerosol modules. So how do you see those two, like gas phase and aerosols, working separately? They should be in all models put together, right? Right now, they're being solved separately in many models. In CAMP, they're being solved together, which is better.
As a software engineer, I cannot speak to what it is you would like to do in terms of science. I would expect that you would want to solve them together, but that's something the community would want to decide. If you want to solve them differently, you can separately, you can continue to do that with something like CAMP.
Okay.
I can see.
I mean, the wish is to have them together, but yeah, sorry.
I can see the advantages to having it separate so that you can plug them. You know, you can unit test various aerosol approaches without necessarily changing the way you're solving the chemistry. If you could have a coupling frequency that maybe, you know, is short enough that you don't see issues with separation.
It can be configured that way if you want.
I'd point out too that in CAMP, you know, you can solve the partitioning along with the gas phase and condensed phase chemistry, but you don't have to. You know, you could easily just have a gas phase mechanism and connect to a model just to solve the gas phase portion.
So does anyone from outside NCAR have any questions about Musica, comments, things they're working on we don't know about you'd like to share?
Hi, this is Fa from Argentina. So actually, in addition to this tropospheric halogen scheme I described, we are also working on a polar module. So the implementation of the same processes in polar regions in the Arctic and Antarctica. So this is also being developed in the framework of other ongoing projects. We have some issues. I mean, we have the model already set up for present day conditions, but then we need some help on addressing some changes on sea ice coverage and stuff like that for climate simulations, and that's something that we need to work in the future.
Excellent. That'd be great. I think Pablo's asking about the relative cost of WRF-Chem to Musica. We think it's comparable for the same resolution. We've been trying to do some calculations to compare them. But once you do the regionally refined, that's generally the majority of the grid points. So having the whole globe is just, you know, a fraction of the grid points. So we think it's very comparable costs. And then you don't have to worry about boundary conditions and those sorts of things. So.
So I guess there's a pause there. So maybe I want to circle back to Baruz's results over Australia in the unrefined region. And I think that might raise an interesting question and something that needs to be explored and maybe fully understood. I think because if I looked at the graphs right, it looked like he did rotate the NE30 grid that's uniform. So it's not the grid rotation, it's not the damping the scheme that's being applied. And I think Adam might be right that the difference there is going to be that the time stepping is different. And so if you have a refined grid and you have a higher or shorter time step, and you're comparing results outside of that refined region with a uniform grid, then if those differences are due to the time step, then there's going to be a lot of care in interpreting results outside of those refined regions. So it'd be worth maybe Baruch says go ahead and rerun that uniform NE30 with the same time stepping that's used in the refined grid, and see if those differences go away. And if so, then that's something that I think needs to be documented.
Yeah, that's good. Thanks.
Thanks, Patrick and Adam, for your insights. Yeah, I would definitely do that.
Anything else?
I'd just like to make a comment that I think this the HEMCO infrastructure could be generalized. I'll sort of put this in the comments that I think that there's a real opportunity here to think about if all the infrastructure is there to read in a file and to regrid it on as needed and interpolate it in time and then provide it through the physics buffer, that all that infrastructure would be ideal for just a regular CAM run where you need to specify the radially active species. But if you can ingrain this infrastructure and have it sort of as its own module, that maybe the regridding can utilize GPUs and that sort of thing, that really, it's a way of getting chemistry infrastructure into the CAM infrastructure and being updated all the time and extendable. And why have separate, if really the only difference is that you're specifying per cubic centimeter as opposed to per cubic centimeter per second, then this seems like a great opportunity to start to think about unifying and integrating the software into the whole of the model.
Yeah, I think we're definitely in conversations on the work that Patrick has started doing in doing online regridding of the MET data and having, and recognizing we're reading in a lot of files in CAM and be able to unify how this is all done is definitely a goal. Did you want to say something more, Haipeng?
Hi, and well, yes, I think everything has been covered. It would be really nice to utilize HEMCO's capabilities to also to retrieve data beyond emissions. That'll be a really good opportunity. We're already doing that in offline GeosChem. So we've replaced all the NetCDF inputs with data flowing through HEMCO so that it can do the regridding and subsetting in just one place. So it will be really useful to incorporate this into CESM.
I'll answer Maria's comment. I think Tim Butler and Aura Lupascu are thinking about running Musica over Europe, and there should not be any issue with running over the Greenwich Meridian, but we definitely should get together and discuss that and help you guys get started with a Europe grid. That would be exciting. And since it is afternoon at noon in Mountain Time, and we are going to get together in an hour for the wrap-up session, I hope you can come back and join and voice your opinions and comments about how we can, what the priorities are for development and making sure that chemistry is considered in all of these developments. That would be great. And so there'll be some breakout sessions, hopefully, to address the same questions. So hopefully everybody will get a chance to say what they'd like to say. If you have any specific questions about Musica and CAM-chem, please feel free to email me or Simone and look at our wiki page. We're happy to help. And tomorrow, if you want to get a walkthrough on making your own regionally refined grid, please join Patrick's tutorial. He's given this a couple of times. He does an excellent job. And we'll be posting the recording of that online and augmenting our comments, our documentation on the websites and wikis to help people get started with making their own grids. So thank you, everyone. Hope to see you in an hour and at the next CESM workshop.
Thank you, Luisa. Bye. See you.
Thanks.
Thanks, everybody.
Hi, Louisa. It's Elizabeth. Do you have an agenda slide, or would you like me to put one up while we're on break?
Oh, for the breakout session?
Just as like a screen placeholder, since the YouTube stream stays open while we're taking a break on the agenda.
Okay, I didn't, oh, no, I don't have that.
Okay, I
have my PowerPoint here. I can paste that in. Did you make a folder for today's presentations?
Yes.
Did you share it with me? I couldn't find it.
I may not have, so I apologize. I learned from last year and have a different folder for every day. Otherwise, it makes me a little crazy when I go to do the uploading. Here you go.
And I guess we'll get together and try out the uh, 10 minutes before 1 to check out what we're gonna.
I saw that, sure.
See how many people join us and okay, that looks all right. Share screen.
We did get a high of 72 people at one point this morning.
Well, I think that's the most we've ever had for a chemistry climate.
That's pretty exciting.
Working group. We usually have about 15. So that's nice. Does that look okay?
Yes, that's perfect.
All right. Mountain time. Okay, so I think everybody knows what's going on by now, but
okay, I'll see you in a bit.
Yeah, I have to go get some lunch. Good, thank you.
You're welcome.
Aye.
Aye.
Do you think we should all just, I don't know, download a copy of the questions and kind of edit them locally, or what do you think?
Oh, yeah, either way.
All right.
So Julio, do you know how people are going to get assigned to each breakout group?
Yeah, it's going to be kind of a free for all, and we're going to ask people to not join groups that have more than, I mean, we'll see how many people join and then divide by how many groups there are, and ask people not to, you know, not to join groups that already have the kind of the uniform distribution of members.
Sounds good.
So that's how we were going to do it.
Hi.
Aye.
You got back your best room?
Yeah.
Your better office?
I'm back in the nice room now. Yeah.
Yeah.
Only for the hour though.
Okay. Then is there an update of the document that say that you want us to update immediately in the Google slide?
I thought it would be easier if
I think it's easier because then, but then every group. Let me go back to your document. I think it's easier because then everybody, you can use the slide after for the final discussion.
So you'd like using the Google Slides?
Yeah, it's what I was thinking. Yeah, isn't it what you Julio was thinking? It's easier.
Well, I was advocating that everybody copy a local copy, but
okay, we do a local copy and then we send it back or we present it. Okay, it's fine with me. I just want to know what I need to do.
That would be, I mean, to me, that seems easier than.
Okay, let's do this then.
You know,
let's do this. Yeah.
I don't have strong opinions on that.
Okay, but let's do this. Yeah.
Okay. So
it might be easier because then, yeah, you will have only to deal with just your pages and it's not too long. Then
we have a kind of a something from each group.
Yeah. Okay. And then what? Yeah, did you decide how you divide the group or?
Yeah, well, we're trusting people to be, you know, considerate and not stack one group compared to another.
Okay.
But other than that, allow them to, you know, just join whatever group they want to join.
Okay. But the group all answer the same set of questions.
That was my.
Yeah, no, I think it makes sense.
I mean, you know, I don't think everybody had, you know, certainly there are a lot of questions here, and I would expect that many groups won't get to more than one or two. And yeah, I think these are more, I guess these were more to get people thinking about the same things, but.
Yeah. Okay.
So do you want to present those? So when we're explaining what we're going to do?
Yeah, I'll present at the beginning, and yeah, and then we can send people off.
I slightly updated page 2, but nothing major. Yeah.
Oh, did you just update it now? Or?
20 minutes ago, maybe. Yeah.
Okay. Yeah, I just downloaded it a minute ago.
I just downloaded it.
Okay. That should be fine.
And so for the report back, how long do you think each of us should talk?
I was thinking no more than a minute or two.
Oh.
Do you think that's reasonable. I didn't want to have our reports take up the rest of the discussion.
I think it's great. I think it's hard to open your mouth and say anything in less than 2 minutes, but I think we should try.
Yeah.
I also need to run out at 4 p.m. my time, so 2 p.m. your time.
Oh, no.
Yeah, so conflict.
It's been a long meeting. At 2, we're done, I think.
Yeah, okay.
Yeah.
My feeling. What I'm not sure about is, okay, there's Nick Penatella. I haven't seen, oh, and Xiao Hong, are you on board with this whole thing?
Yes, I'm here.
Okay, all right.
Okay.
So the plan is to have breakout, each of the co-chairs will be in a different breakout group, and we'll ask everybody to just divide themselves into those breakout groups, just so there's not too many people in any one, and everybody will discuss these same questions. Was our plan. And maybe we'll see how many people there actually are to decide how many breakout groups we really need.
Yeah, right now we have 18, so.
So Julio, you say you are going to present these 3 slides to the whole group, then we break up to the different breakout.
I would download a copy to your own computer so you can share it with your group.
Okay.
I'll show them at the beginning, and then if you don't mind sort of discussing, at least trying to discuss some of those questions in your breakout group. And then after 15 minutes, we'll reconvene, and the co-chairs will kind of try to summarize the discussions in their breakouts.
Okay, sounds good.
After that.
Mm-hmm.
So Elizabeth, all us co-chairs will be assigned, right? We'll just be sent to a breakout room.
Yes, co-chairs are already assigned.
Okay.
And then I'll distribute everyone else.
Okay.
Okay. And I'd say, maybe after 20 minutes, we should all be back. But I'd say after 15 minutes, we should get some kind of warning or something, right?
Okay, then after 20 minutes, because I think
take,
the moderator should give the warning.
Yeah, I'm just thinking it might take a few minutes for the groups to kind of settle down and get organized.
Yeah. Then, Elizabeth, are you able to send a warning, more than 1 minute warning, or?
Yes.
Okay.
A
5-minute warning you want? Okay.
What do you want, Julio?
Yeah, I think that's good. 5-minute warning, and then we'll
5 minutes, and then 2 minutes, and then
we'll just then enforce it.
Good. Yeah. So I thought Elizabeth just said that she was going to automatically assign everybody to groups instead of them choosing their own group. Is that true?
Or would you?
Yeah, it's what she just said.
Or do you want everyone to choose? That's fine too.
Oh, I'm actually happier if you assign all the participants in the session to a group. To me, that's a better solution. I thought I thought that was difficult for some reason, but if you can do that, I think that would be the best. Does everybody agree?
Yeah, I think it's better because then it's more distributed. You don't have like random number of people showing in a single room.
Okay, so that's good.
Could you make me not a co-host, please?
Sure.
Because I don't see the right things.
Okay.
Okay. I'm going to go ahead and start sharing my screen.
I have one more question then. Sure. Elizabeth, then you will stay there if people join late to send them to... Okay, thank you. Yeah, it was just to know.
Yeah,
okay.
I'll send everybody off and...
Okay.
How many groups do we have at the moment? Or are planned to be there?
I've got 7.
Okay.
7 groups. Okay, so we're approaching 35, so that would be 5 per group, which is becoming reasonable. No, we're up to 35, so I think we've passed the threshold of 7 groups.
You have 7 group or 8 group? Oh, yeah. Oh.
Elizabeth said 7.
Okay.
Okay. Well, thanks to everyone who has rejoined for the discussion. I'm going to share some questions for discussion. Of course, nobody, you guys are, feel free to raise other questions, but I thought I would just share some of the questions that some of the co-chairs and I have put together as, a possible interest. So the way this is going to work, we're going to wait a little bit to give people a chance to join, and then we're going to split off into breakout groups that will be assigned by Elizabeth. And those breakout groups will they'll talk for 15 to 20 minutes. Then the the moderator, co-chair of the breakout group will be sort of noting the discussion, or listening to the discussion, and we'll reconvene after 20 minutes or so, get a quick presentation from the co-chairs, moderators, and have a further discussion after we've heard from the breakout groups. So I'd say we wait till maybe 1:05 or so. I put the questions up there. You should be able to see them on your screen. So there's 2 pages. It's a lot of questions. And as I said, you all should feel free to, answer the ones that you're interested in or come up with different ones. But, one theme that has been sort of coming up over and over in this meeting is a common theme in our meetings, which is that we at NCAR, feel pulled between supporting kind of a cutting edge science model, but also supporting options that people with more limited computer resources might be interested in, et cetera. So that's one topic. in the past, in our previous queries of the community, we've heard that people want more tools and capabilities to sort of tailor their own configurations. Then on page 2, there are more specifics, what resolutions we use. We've also heard a lot about GPUs in this meeting, and I know that there are already some efforts going on to integrate GPUs into the CSM, CAM infrastructure. I'm wondering, how AMWG should, or if it should address this. Is it okay to just have it sort of bubble up, or should we have, some kind of structure in place, some sort of team? Vertical resolution and DICOR, I think, have done pretty well with targeted teams. Do you guys think that would be useful to have for machine learning and GPU issues? And finally, kind of a repeat of a question on the previous page. If you're not interested in long climate runs, what do you, what would you like to see? What capabilities are you interested in having? Okay, so it's 1:05. I think we should probably just go ahead and start sending people off into breakout groups. If people join late, can you assign them to a breakout group, Elizabeth?
Yes, I can see the number of people in each room. Right now we have 6 or 7, so I'll just do my best to keep the balance even. Okay. So in 1 second, if we're all ready, I'll open the rooms, and so you'll see an invite to join your particular room with one of the co-chairs.
Okay, and in about 20 minutes, we'll all be brought back or come back.
Yeah, I'll send you some countdown warnings.
All right, thank you.
So, Elizabeth, quick one.
Yes.
Will this stay on these slides stay on our screen in the breakouts?
Each co-chair will share them.
Oh, okay, they'll have them. Okay, sorry.
Yeah, I should say too, that if you have any chat in your breakout rooms and you share some resources and you want to save them, go ahead and do that.
Okay.
Just to make sure that anything is captured that you need.
Right.
And I'll be here in the main room, and anyone who needs me can summon the host. And so then I can pop in and answer any questions if you have them.
Okay.
Okay. Go ahead and join your rooms. Hi, for anyone here in the main room, you'll see an invite to join your breakout room. So go ahead and click that and you'll be sent off to meet with one of the co-chairs.
So
Were we supposed to get kicked out?
Yes.
Oh, okay. That didn't seem like very much time.
The 5-minute warning was very short.
Yeah, I don't think it was 5 minutes, but
Yeah.
It was 30 seconds.
Thanks for taking notes, Nick.
Oh, sure. Hopefully I
Yes.
captured most of the discussion.
yeah, 15 minutes to 20 minutes didn't seem like very much time at all.
I was really watching the clock, honestly.
Yeah. I know. I see my clock on my computer. It was 20 minutes.
And you know, it's nice to see everybody on having their camera run now after the breakout groups. It's nice to see everybody.
So is everybody back?
Yes.
Okay. So should we just go ahead and start sort of rapporteuring from the breakouts?
Yeah, I think we should.
Okay. So I'll go ahead. I'll go ahead and start. I think I'll be fairly quick. So my group did not include very many modelers per se. So they had a different sort of take on things. We did have one modeler join us later, and well, Han Lee, who was obviously a modeler. So like I said, I thought we had some different takes. The members of the group did not necessarily want to do, they weren't interested in doing long climate runs. The observationalists in the group both sort of expressed an interest in having both high horizontal resolution and vertical resolution, maybe with vertical resolutions, maybe with variable resolution meshes with nudging. There was a pretty strong support for having higher vertical resolution. There was even a talk, or there was some interest in having higher vertical resolutions than we're considering already. So even higher than 500 meters. Han Lee brought up a good point that not only do we need tools for vertical grid generation that are easy to use, but especially for deep models, having some way of spinning up initial conditions at these higher vertical resolutions, deeper grids is very important. And we discussed a little bit, we discussed what what sort of people outside the immediate development group at NCAR should do on their own. There was a little bit of skepticism about whether tuning is something that people should undertake. It was thought maybe tuning is not straightforward. So I'm gonna leave it there and go on. We should go on to the other groups.
I'm happy to go next. I took analog notes, so I can't share my screen.
Mm-hmm.
So I think we actually, instead of talking in particular about some configurations, it seemed like the main point of view, at least in terms of the first question, is that NCAR should really be the one to decide what they are able to support, and should actually see their role as sort of pitching to the community, the costs and benefits of different model configurations, and basically coming up with their own sort of plan based on the resources that they have, and present that to the community instead of necessarily the other way around, sort of, because you can always, get 10, 20 different answers for what someone wants out of a model configuration. But if you give them a few decisions, they can probably come to a good educated decision. We talked about the trade-offs between cutting edge and scientifically validated and usable model simulations, and how the needs of someone doing long paleoclimate integrations is quite a bit different from someone doing shorter high resolution integrations. That there's a confluence of university users and external users who want lower cost models, but then of course also people internally who want lower cost models as well. There was a desire for a better and more defined pipeline for contributing modifications or additions to the model. And then in terms of, just revisiting that sort of first question, it's impossible to answer really what NCAR should do in terms of particular model configurations, and it needs to be framed as discrete options. And I think we were really struggling at the end to decide, can NCAR afford to carry all these different model simulations, or does it really need to choose a niche model configuration and kind of roll with that as a flagship? Because there's an argument that we can do everything mediocre, or we can choose one thing to do really well.
Right.
But then, of course, there's always the issue of putting all your eggs into one basket that we started to talk about at the end too. So I don't know if we had a really obvious answer, but just that I think maybe NCAR needs to come to the table with a better description of what it can do and the options for the community.
Okay.
I don't know if anyone else is in that group thinks I left anything out, definitely chime in.
Let me maybe go next. And I think this was similar to Nick's comments. So we raised the point that NCAR might be pretty much constrained what they can support in terms of model configurations. We saw a need for frontier applications, these cloud resolving applications that need to be GPU enabled, and saw immediately the dilemma that these codes become impossible to read, especially for grad students that maybe want to get their hands dirty. So the new technologies and the new computer architectures make it really hard for newcomers. We also see the need for a mainstream configuration that could be the 1 degree typical climate simulation and the simpler model hierarchy. And the question became, what can NCAR support in a reasonable fashion, because tuning becomes prohibitive. We already see the need for different tunings at high top and low top models, for example. So NCAR and AMP maybe needs to strategize about that with the community. We had strong support for variable resolution as also a workhorse tool for the community, which also is a bridge to the high resolution. We really want, and Patrick was in our group, he confirmed that tools are now mainstream for the community to use to enable them to use variable resolution. And we had support for higher tops and higher vertical resolution, but it was questioned whether 500 meters is necessary, and maybe 700 meters would be a good compromise.
That's interesting.
Stop here.
Okay, I can go next if nobody else will. So I tried to really boil down the things that we had. So one of them was that we were struck by how almost everyone wanted a different configuration for their science. And so this idea of having one version of the model doesn't really seem consistent with the idea of having a community model, in the sense that a lot of times the cutting edge involves running in a different configuration than other people have before. So we didn't really discuss how challenging it is to for NCAR to support a lot of different configurations, and just said that we think that a lot of different configurations are important for the health of the community or system model. And in that regard, we didn't talk about this, but I think that SEMA might be a good thing in terms of enabling more configurations more easily, given NCAR's constraints. And then another thing that we talked about was just how CMIP is really driving a lot of model development, and a lot of what AMWG typically does is focused on having this great kind of workhorse version, but that maybe that should be a slimmed down sort of a working group, and that there should be other working groups to do more of the kind of, I guess, bespoke different things that we're trying to do with the model. So acknowledging that CMIP is important, but also that it's not the only thing. So I think those are the main points.
Real interesting. Thanks.
I can go next if you want.
Sure.
I will just share the notes here. So a lot of the things I think are quite similar to what's already been said, but a few thoughts. Again, it's very difficult to plan for the future in terms of what can really be supported. You don't want to limit yourself because new things and developments will come along. And the general thought is, it's commented that it's maybe best to consistently support a model that is the most general and applicable to the widest set of people versus if you develop and focus all your attention on a sort of niche configuration, then it's really maybe not having the widest application in terms of supporting a broad group of users. And it was mentioned that there's a need to kind of balance development for the state-of-the-art model that's largely focused on the CMIP simulations with support for simpler models that can serve the communities. And in terms of what could be supported, there was at least mentioned, could CSM and CAM become more similar to WRF, where the configuration is largely specified and set by the user, and not really these sort of set specific use cases as currently done. But that would require a lot of development and support in terms of educational resources, so people aren't creating configurations that aren't really going to work for their scientific goals, right? You could imagine you want to study something and you don't know where to start in terms of how to set everything up. So there's some advantage in the current setup in terms of having a set specific use cases, but that does provide some limitations. And then in terms of user community, they very much support maintaining and supporting older models, because the increasing computational cost of new models becomes limiting. So they might want to use an older version of CAM and CSM because it's computationally more efficient, and then the new advances in new models may not be directly relevant. So there's not a strong motivation always to move to a new model, and also just it's a little bit easier maybe for graduate students to understand older models that have a bit less complexity. And this maybe ties into the issue with GPUs, that the coding for that just makes it less readable. So for a student to really understand what's going on in code may be even more difficult in that sense.
Okay.
Okay, so that'll leave me. We spent a bit of time on clarifying questions such as we are not unifying CAM and WACCM, that they will still remain distinct, which sort of led into the conclusion that maybe we really need a higher resolution, more detailed, higher horizontal and vertical resolution model, but also a coarser resolution, cheaper version of the model. That would probably be helpful for the community. And another thing that was brought up was whether all the possible diagnostics are really being considered in the evaluation of the, particularly in the new vertical levels, and is sufficient chemistry being included in those diagnostics and those evaluations. And so I think maybe as a group, we should think more about also about all the diagnostics that should go into evaluating all of these new configurations before we make a decision.
Thanks.
So that's all.
Great, thank you.
Okay, then maybe.
Oh, do you have one?
Yeah, I will go next. Then I was in a group with Simon, Adam, Thomas, Rebecca, and Meg. And then we talk a little bit about issue that Thomas at his institution, and that should be similar to university that run on smaller machine. He used a smaller machine than Cheyenne, and for him it's very challenging to do the simulation he wants to do. For his work, he needs to run WACCM at 1 degree. He needs both the iTop and the chemistry. And he wants to do simulation of the order of 300 years, and he will do 3 ensemble. And his machine is not enough to do this, then it's very challenging, and often he's forced to run 2 degree simulation, even that he really need the 1 degree to represent the baroclinic storm evolution. Then we discuss a little bit what people would be willing to sacrifice to help with this, because basically anything we can save would be good, even if it's like 5%, 10%. Then Adam was suggesting that maybe we should use the NE30 PG2. It would be an option because we could save 20% with this. Also, we talk about the fact that CAM is much more expensive than other model, 2 or 3 times more expensive than other model. And maybe some people would be willing to go back to CAM5 or WACCM 5 to do their work. It seems WACCM 4 would not be enough, but to go to a physics that's cheaper would be a solution for them. And then Rebecca, she's not running a long climate simulation. She does more regional impact studies. And yeah, I think it's what we had in our group. Anybody in my group want to add something that I forgot?
So just for, I just want to clarify, when you said that the model is 2 or 3 times more expensive, you guys are talking about CAM6 versus earlier versions of CAM?
No, CAM versus ECMWF or other model, yeah. Okay. Yeah. I don't know which model, Thomas, if you want to comment on which model you were referring to, but not compared to CAM5, compared to other models.
Other Earth system models.
Yeah.
All right.
Well, I should say maybe other forecast models.
Okay.
Yeah.
Right.
So what happened recently, for example, is that other components in CAM also became more expensive. And and that has added to the cost as well.
So I think we also talked about the GPU.
Oh yeah, it's true.
And that may be something that even your machine may be improving, so the speed of the model, or it may be even feasible eventually if those options are also with your machine available. And if the model is, work towards those, that may be a different question then, if you can run it or not. Yeah, I think one more point was that we also talked about consistency in people producing data sets that are used for like WRF input data, and changing, in terms of consistency and what is here and what will be in the future. Having a new model, those data sets will have to be reproduced, and that could require additional resources and costs.
We also,
go ahead. I was just wondering if there was another group that had Was there another group, Elizabeth?
No, that's everyone.
Oh, okay. So go ahead, Adam. Sorry.
I was just going to make a point. We also talked about how SYPD is not the right metric because of depends on your resources. So core hours per simulated year is independent of resources, so probably a better metric.
Okay. That's a good point.
And I see that Kevin also has a comment in the chat.
Yeah, Kevin Rader is interested in hearing from the university community about applying for allocations on Cheyenne. He's heard that the university fraction of Cheyenne is underused, and he's pointing out that would help people with increasingly expensive model. So, are there anybody from the university community want to comment on the application process for Cheyenne allocations, whether you use them? I mean, is it an attractive thing for the university community, or do you prefer running on your local machines? If Kevin has, if he wants to sort of go into more detail about things he's interested in hearing, he should speak up. But
I would like to comment on that from a university perspective. So the big caveat and stumbling block is that you do need an NSF grant to justify this allocation request. And if you don't have that, you can't do it. So NSF is very reluctant to support efforts on the university side in terms of model development. So if you do model development and you do it with DOE funds or other funds, you can't use the Cheyenne machine, although it might be CSM focused. I think that's a dilemma for the university.
Right, but maybe the other Kevin R can maybe provide additional context. But it's my understanding that by underused, do you mean that the actual percentage of resources used is different than what's allocated? Or are you saying that they can't meet the allocation of the percentage of the machine they've saved for university projects? Or do you know? Because those would be two different things. Oh, you're on mute, Kevin.
Thanks. Sorry about that. My impression is that over the course of a year, fewer core hours are used by the university community than could be used. I think that the distribution of the use is skewed a lot. There's very heavy usage in the fall, for instance, and approaching the conferences like AGU and AMS. But overall, I think that there are resources there that are not being used yet. And I don't know what the challenges are to use them. I appreciate Christiana's pointing out that you need an NSF grant. But I'm interested in other roadblocks and hurdles.
so being a member of the UCAR consortium is not enough to apply for a university allocation. You have to have a funded NSF grant.
To apply for a large allocation, so anything over X amount of core hours. If you have a graduate student or a postdoc or your early career faculty, you can apply just by being part of UCAR consortium. You can apply for resources.
Okay. We're getting close. We're getting close to 2 o'clock. I really appreciate all the input from everybody, as I'm sure all the other co-chairs do. Not many people commented on the GPU machine learning question. I know that I get sort of overwhelmed by those topics. I'm wondering whether, before we break, does anybody want to offer any opinions or advice on how we should approach the issues of programming for GPUs and using machine learning? Is this something that's really just best left to bubble up from the community, or, you know, should there be a task force, et cetera?
I guess I have a couple of comments about that. So I guess I don't see there being a ton of connection between GPUs and machine learning, other than that
No? Okay.
machine learning works well on GPUs, so it's a use of it. But I also think that the idea of having GPU capability bubble up from the community is pretty unrealistic. I think it's something that's really a software engineering task, and it's not particularly fun cutting edge science to do. So I think that it is exactly the kind of thing that NCAR infrastructure needs to do if it's going to happen, rather than counting on anyone in the community doing it for us.
And we had that discussion in our group. It was raised that NCAR actually doesn't have any resources to do that, and it's currently supported by an external grant. I guess Earthworks has this on the, I guess, on the agenda, which I think is concerning. So I think NCAR should also internally get together and make a strategy or formulate a strategy. What is the GPU support for the future, and what is maybe a machine learning activity that NCAR wants to. I know there are pockets that already happen currently, but I think there's an opportunity here to explore machine learning capabilities for the Earth system scientists, and NCAR should be, I know they are affiliated with some activities, but also should formulate their own strategic view.
Okay.
With the community, yes.
So my understanding is that the CESL is ramping up on their skill in terms of how to port things to GPUs. And I assume that part of their support will be to enable people to port their codes over to use the GPU. So I don't know if it's fair to say that NCAR is only supporting GPU development externally on external funds. I think it's part of CESL's job is to support the use of their machine. So that facility will be there. Whether or not they're going to give you a software engineer to take your code and turn it onto a GPU for you personally is, maybe not, that won't be there, but I'm sure there'll be their support to help in migrating things.
Okay, I see that Joan Alexander and Andrew Gettleman have their hands up. Why don't you go ahead, Joan, and then
I think this is quick. This is about machine learning applications for physics. I'm involved in one project, and I know there are a lot of people involved in machine learning, development of machine learning tools that would have applications for physics parameterizations. And I think a stumbling block is translating those codes into Fortran to use in the model. And I just think I would wonder if NCAR could help with that side of the equation.
Okay.
I'll comment on both those two things. I think I mentioned this earlier. We have that code. We've actually put neural networks into the Fortran and called them from parameterization. So I don't know exactly what our plan is for rolling that out, but if that's something this group wants, we can do that. We may actually be putting it into the microphysics anyway in the baseline model, in which case you can see it. But that's number one. I guess also on the topic of machine learning, to comment on Christian's question, I think CESL's ramping up in a variety of different ways, as was said. I don't know that machine learning to me strikes me as like it's a tool and it can be used for lots of different things. So I think it's hard to have an overall strategy, except yes, we're promoting it and we're trying to figure out how to do it in a research context, because there's lots of different ways it can be used. Right. What we just talked about one, which is actually putting it into the model in Fortran, but that's totally different than some of the other applications, say for data mining with machine learning. So I think there is a lot of work in CESL on, there is, I think, a machine learning strategy, but I think it's not, we're going here. I think it's letting a lot of things bubble up and supporting the research community. GPUs, going back to what Dan said in some of the earlier comments, we are engaged in this effort. We're slowly learning how to do this within AMP. I've actually been talking to CESL this week about essentially ACC for dummies. So how to actually look at code which has ACC directives and how not to break it if you're modifying it, and how to like work with it. So it's sort of like, if you're given code, we can develop it further, and we can also some ideas about how to write code that it's just retraining a whole community. And so, as Dan said, CESL is going to be doing that as we roll out the new machine. They're already ramping up, and they realize you don't just buy the hardware and let it go. You buy the hardware and you have to support the hardware, and they are ramping up to do that with our community model. So I think by the time the new machine arrives in a year, we'll be a lot farther along that strategy, and we'll have a lot more tools that we can provide people to as the model starts to move into there, and we actually have a machine that can be used extensively for GPU work.
So the idea is that CESL will provide training or training sessions for people?
I think so. I mean, there's already, there was an advertisement, CESL advertised this Pittsburgh Supercomputing Center is running a similar, day-long introduction to OpenACC or ACC, which is basically the programming for the GPU architecture we're getting. CESL's, I think, going to run some workshops. They're obviously going to be virtual. They will obviously be recorded. And so I think I've been encouraging them to have one, not just for software engineers, but one for scientists. Like, here's how to hack code, which is written for GPUs. So I think, yes, the answer is they're moving in that direction. And I think by the time the machine arrives, there'll be a lot more of that happens in the next year.
Are there any other issues people would like to bring up before we close?
Yeah, I would like to, I guess, address the tuning problem. This kind of has come up in the musical group when we've been going through the variable resolution tutorial practice sessions, and so it turns out as people, everyone's like making their grids, and they're all trying to solve the same problem at the same time. How do I tune this grid to do this? And so the idea was that maybe we'd have like a forum, a community-driven forum, where everyone, once they get their grid set up, would add it to a database. And I guess I've envisioned something like back in the golden era of CPU development, when they have the benchmark pages where people would have, here's the benchmark of my CPU and here's the configuration of my machine. Something along those lines, where there's a database that people can browse through, over the internet, where they can look through and browse through other grids that are similar to what they're developing, and then use those tuning parameters that have been established as a guide, so they're not having to solve the same problem over and over again.
What sort of tuning issues are coming up in variable resolution?
Well, how do you set the time step? How do you set, all the things to make it stable and to get a good run?
Okay.
People don't have to go through that whole experience of iterating and coming up with the solution that someone else has already, come across.
So this isn't always tuning for climate performance. It's tuning for stability and things like that.
Well, I guess I think it would maybe fit into maybe a broader, I was thinking in terms of the resolution stuff, but maybe the idea fits into a broader, context of other issues in terms of climate variability or, stability. So I guess, the idea was, maybe have a bulletin board, but, there was some concern about having, that maybe the bulletin board, CSM bulletin board wasn't the right place for it. So it's something that's ongoing, trying to figure out. And I think that finding the right way to do it and the right place to host it is kind of the issue right now. But I think it would be a benefit for everyone to have a common resource that everyone can contribute to, and then learn from each other's experiences and save a lot of effort and headaches and CPU time.
All right.
I mean, we should, Professor Rich, probably kind of look at what WRF does, because this is as close to a kind of operation as WRF does in terms of setting up different domains, really, and then hopefully they give some advice with relation to, time step versus grid size, etc.
Do they have something similar?
I don't know. I'm completely. I mean, they have obviously a few bulletin boards, but surely people are setting these things up all the time, and surely they have something kind of that helps people do this.
Yeah, I think that came up in some of the in one of the comments, I believe, that yeah, if we are going to rely on the community to do lots of tuning, there's going to have to be more support.
Yeah, we should definitely be aware that tuning means different things to different people. But
Right.
there's an awful lot of configurations of this model that do not require tuning.
Mm-hmm.
A lot of the chemistry runs are done with specified dynamics. The space weather applications don't require top of the atmosphere balance. You know, S to D, or at least S to S. You know, we don't need stability over 100 years in our control runs for that. You know, so let's not say, well, we shouldn't support model configurations because the model is difficult to tune. You know, maybe it's all we need is the tuning to get it stable, and it just needs to be tunable to be fit for purpose.
Great, those are great points. Thanks.
I think that, you know, there might be some overlap from that document that I sent you this morning, Pat, where I set up a document recommending what time steps people should be using for variable resolution grids. And so, I don't know, maybe we could build off of that. You know, obviously, one question is the form, where do we put this, and then the substance. And I think that we could probably build off in terms of substance-wise from the document I created.
Yeah, and I was going to suggest, you know, tomorrow I was going to suggest that kind of as a starting point, you know, that what you have there, and that, you know, that people can like build off of that and then add to it. And then, yeah, so we can all learn from each other.
Okay, so thank you, Patrick and Adam. So it's almost 2:05. Thomas, you'll have the last word. I think we'll close after Thomas, because I do want to respect people's time.
Thank you, Julio. I'll be very short. One of the great things I like about CAM is that there is so much ongoing development and really good science going into that. And a lot of that is the contribution of academia and users from outside NCAR as well. So one thing that I would just advocate, which is already the case, but is good to keep as well, is to allow CAM to be hackable, so that users can actually play with it and can make changes to, you know, various aspects of the model configuration without becoming crazy about the technical aspects, or without having to fight maybe some part of the code that are hardwired to a specific choice of parameterization of parameters.
Or hardware. Or...
Yeah, but also machine learning has the danger of you know, of being set up for one configuration and not to work well for other things. So so I really enjoy working with CAM because it's fun, and that's maybe something to take into consideration also for the rest of the academic community, because it's good code in that sense. Sorry, I should shut up now.
Well, thank you. Thanks for the comment. And I really think I want to thank everyone for sticking it out this long. It's been a long meeting, and many of you will still be attending the regional refined workshop tomorrow. So I will let you go now. And thanks for the comments. I really enjoyed this meeting, and I hope we'll see each other face to face soon. Thank you.
Thanks, Julio.
Thanks, Julio.
Bye-bye.
Thanks, Julio. Thank you. Bye.
Thank you.
Thank you.
Then Julio, do you want me to send you the document?
Sure.
The slide, yeah.
Anybody that has notes, yeah.
Yeah, I took notes, and yeah, I will send it to you now. Yeah.
Okay.
Yeah, and then yeah, it was funny because Choang was supposed to. Then first, I didn't end up with a room. I don't know. I think Elizabeth just set the co-chair.
Okay.
But then Choang didn't show up.
Oh no. Okay.
Yeah. Then it was fine. Then at the end, I had a room. But yeah.
Okay.
It was why I was asking why you had only 7 group, Elizabeth. because yet Julio had assigned other people.
Okay, yeah, no, yeah.
Yeah,
I
and I
think
should
the
have
number of-
insisted. But I think it was perfect. Yeah.
No, the number of group, it wound up perfectly fine.
Yeah.
Cecile, that's exactly. I had you as a room, and then I heard Julio say about the co-chairs, but I already had you in a room, and so when I put Xiaoheng there, so I'm glad that it worked out. And Julio, you had a couple less people because people showed up in the participant list, but they weren't actually there. Like I had assigned them to your room.
Uh-huh. And
so
then
they were there theoretically, but not actually in person.
And we had Walter Hanna joined our breakout without wanting to.
Oh,
who was it?
Walter Hanna.
How does it? He was.
Well, he popped up a little bit later, so I just
he got in a little late, and then he clicked on the link, and it sent him into my breakout. I guess there was an overlap between the address or something, but it worked out fine. It was great.
Yeah, it's funny.
Yeah, and I really was watching the clock when Monica said it didn't seem like it, and I'm like, oh, I was careful.
No, I think it's just that it goes very fast. I don't think she was telling that you didn't respect the time. I think she just said that it feels that it went really fast.
I noticed when we started and we stopped about 20 minutes.
No, you did the time. I think nobody had question about this. It was just that it felt we covered two questions. And I was just trying to
Yeah,
I mean, there were a
great
lot of
though.
You
had 50 people for the wrap up, which was really amazing. 70. I've been keeping a little tally as we go along. 72 this morning, 50 this afternoon.
Yeah.
And 60 tomorrow for the VR workshop. Right?
Yeah, that might have gone up even since.
Yeah. I know.
70. You made number 70 when you registered this afternoon, Julio.
Okay.
I was going to send it to you anyway. Don't you
worry.
I know.
I just want to listen in.
Yeah, I've got that all prepped, that message prepped to go. I figured I'd just send that when this ended, and we might still have people that register as we go along, through the night and in the morning. It's the same Zoom link that we've been using all week.
Okay. Well, good. There are aspects of having a virtual meeting that I really like. I think it's a lot easier to do breakouts, for example. I think that's a real advantage. And I don't know. I think when we go back to work, we should figure out how to save the good parts of this.
Yeah, it is weird though when you think about standing in a lobby and breathing over other people's food again, though.
I know.
Yeah. I miss this.
Yeah. I miss the human contact.
Yeah. And usually it's when now somebody is going to come in Julio's room and kick him out of the good room, and he will have to go in the basement.
Yeah.
Yeah.
All right.
Okay.
Good. Well, I'm going to work on, I'm doing the meetings in order. So, but next week I only have one meeting, so it should give me a really good chance to get presentations posted. And then if anyone asks you, all the recordings